How space decides what can exist explained slowly. Picture the emptiest place you can imagine. Maybe it's the deep, dark void between galaxies, a perfect vacuum stretching for millions of light years, silent and still. In our minds, space is the ultimate emptiness, a passive, black canvas where the drama of the cosmos plays out. We see it as a vast, silent, and fundamentally empty stage. But that picture is a profound illusion. One of the most intuitive ideas we have about our universe is also one of the most incorrect. The truth is, the void isn't a void at all. It's a seething, churning, unimaginably energetic ocean. And its invisible, intricate structure dictates the fundamental rules for everything we see. From the smallest particle to the largest galaxy, the very fabric of space is what decides what can and cannot exist. What we think of as nothing is, in fact, the ultimate something, the source code of reality itself. The grand question. This raises a question so fundamental it can feel a little dizzying to ask. How? How can something we see as total emptiness be the very thing that governs existence? If the universe is built not on a foundation of nothing, but on a vibrant, hidden architecture, what are the rules of that architecture? How does the fabric of space, this thing we call the vacuum, actively decide which particles get mass, which forces get to operate, and ultimately, why a universe of stars and people can exist at all? To understand this, we need to go on a journey. It's a journey from the clockwork universe of classical physics to the bizarre, probabilistic world of the quantum. We'll have to dismantle our most basic intuitions about reality, piece by piece, and rebuild them into a new, more profound picture. We are going to explore why space is not a passive stage, but an active, decisive player in the game of existence. And we're going to do it slowly. Because to truly grasp this idea is to change the way you see everything. So, let's begin by understanding the old idea we're leaving behind. The comfortable, familiar, and ultimately wrong concept of space as a simple, empty box. The unseen stage, our classical view of space. For thousands of years, humanity has wrestled with the concept of nothingness. The ancient Greeks debated it endlessly. Philosophers like Parmenides argued that a true vacuum, a true nothing, was a logical impossibility. How could nothing exist? If it exists, it must be something. But on the other side, atomists like Democritus proposed that reality was just indivisible atoms moving through an infinite, empty void. Without that void, they argued, motion would be impossible. There'd be no room for the atoms to move. That second idea, of atoms in a void, feels incredibly modern. It's the basic picture many of us learn in school. But for most of history, the opposite view won out. Aristotle, one of the most influential thinkers ever, famously declared that nature abhors a vacuum. He believed space was always filled with some substance, a medium he called the plenum. To him, perfect emptiness was nonsensical. And this wasn't just a philosophical take, it seemed to be backed up by observation. If you try to create a vacuum, like by pulling a piston in a sealed cylinder, you feel a powerful resistance. It feels as if nature itself is fighting back, trying to stop a void from forming. This Aristotelian view dominated science for nearly 2,000 years. The universe was seen as a cozy, filled-in place. It wasn't until the 17th century that this idea started to crack, thanks to scientists like Evangelista Torricelli and his experiments with mercury barometers, which proved a vacuum could exist. But the person who truly defined our classical understanding of space was Sir Isaac Newton. In his revolutionary work, Newton envisioned space as an absolute, unchanging, and infinite container. It was the ultimate reference frame, a fixed, 3D grid. He called it absolute space. In Newton's universe, space was like a giant, invisible stage. It was eternal and inert. It existed independently of anything in it. Whether it held a planet, a star, or nothing at all, the stage itself remained unaffected. It was just the passive background for the laws of motion and gravity. If you could remove every single thing from the universe, you'd be left with Newton's absolute, empty space. A silent, featureless, infinite nothingness. This picture is powerful. It's simple, elegant, and it works incredibly well for our everyday world. It lets us send rockets to the moon, predict the paths of comets, and build bridges. The idea of space as an empty container is a cornerstone of classical mechanics. And for a long, long time, it seemed like the final word. The universe was made of two things: inert, empty space, and the stuff that moved around inside it. But this elegant picture, this perfect separation between the stage and the actors, was about to run into a very serious problem. And that problem was light. The crack in the foundation, a hint of something more. The trouble started with a simple question: how does light travel? In the 19th century, physicists understood that light behaves like a wave. And waves, as far as anyone knew, needed a medium to travel through. Sound waves need air. Ocean waves need water. Take away the medium, and the wave is gone. A bell rung in a vacuum makes no sound. So, if space was a truly empty vacuum, like Newton said, how could light from distant stars possibly reach our eyes? It had to be traveling through something. To solve this, physicists proposed an invisible, all-pervading substance called the luminiferous ether. This ether was imagined to be a massless, transparent, and frictionless medium that filled all of space. It was the ghostly substance that rippled to create light waves. The ether was, in a way, a throwback to Aristotle's idea that nature hates a vacuum. It was an attempt to fill Newton's empty box with something so the physics of light would work. Scientists poured enormous effort into trying to detect this ether. The most famous attempt was the Michelson-Morley experiment in 1887. The logic was simple. If Earth is moving through this stationary ether, we should be able to detect an ether wind, just like you feel a breeze when you stick your hand out of a moving car's window. The speed of light should look slightly different depending on whether it was traveling with the ether wind or against it. But the experiment found nothing. No matter how they angled their equipment or how many times they tried, the speed of light was always the same. There was no ether wind. It was a shocking result that threw physics into crisis. The ether, this thing that had to exist for their theories to make sense, apparently wasn't there. The solution came in 1905 from a young patent clerk named Albert Einstein. With his theory of special relativity, Einstein made a radical proposal. What if there is no ether? What if the speed of light is a fundamental constant of the universe, the same for everyone, no matter how they're moving? This simple but revolutionary idea swept the ether away. Light didn't need a medium. It could travel through a true vacuum. For a moment, it seemed like Newton's empty stage was back. But Einstein was just getting started. 10 years later, with his general theory of relativity, he would change our understanding of space forever. General relativity describes gravity not as a force acting at a distance, as Newton saw it, but as a consequence of the curvature of space itself, or more accurately, a unified, four-dimensional thing called spacetime. According to Einstein, mass and energy tell spacetime how to curve, and that curvature tells mass and energy how to move. A planet orbiting a star isn't being pulled by an invisible string, it's following a straight path through curved space. Suddenly, space was no longer a passive, inert stage. It was an active, dynamic participant. It could be bent, stretched, warped, and even ripple with gravitational waves. This was a monumental shift. Einstein gave space properties. He gave it geometry. But in one key sense, the classical view held on. In a region far from any mass or energy, Einstein's spacetime would be flat and, for all intents and purposes, empty. It was a far more interesting stage than Newton's, sure, but it was still just a stage. The real revolution, the one that would transform that stage into a seething ocean of energy, was yet to come. It would emerge from the strangest, most successful, and most counterintuitive theory ever conceived, quantum mechanics. The quantum revolution. Fields are everything. The world of quantum mechanics is almost comically strange. It's a world where particles can be in multiple places at once and where simply observing something changes it. But beneath all the weirdness lies a central concept that is arguably the most important idea in all of modern physics. It's called quantum field theory, or QFT, and it's the key to understanding how space decides what can exist. To get there, we need to totally upend our idea of a particle. We tend to think of electrons as tiny, fundamental balls of stuff, the ultimate Lego bricks of matter. QFT tells us this is wrong. The most fundamental things in the universe aren't particles. They're fields. What's a field? You're already familiar with the idea. A magnetic field is a great example. It's an invisible region of influence that fills space. You can't see it, but you see its effect when you sprinkle iron filings around a magnet. The field is a property of space itself. Einstein's spacetime is another kind of field, a gravitational field, that describes the geometry of space at every single point. Quantum field theory takes this idea to its ultimate conclusion. It says that everything is a field. Permeating all of space, every nook and cranny of the cosmos, is an electron field. And what we call an electron, that tiny particle we picture, isn't a separate thing moving through the field. It's a localized vibration, a concentrated ripple, an excitation of the field itself. Imagine a vast, perfectly still lake stretching to the horizon. That calm lake is the electron field in its lowest energy state. Now, throw a stone into it. You create a ripple that travels across the surface. That localized disturbance of the water is the particle, the electron. Throw another stone. You get another ripple, another electron. The ripples can interact and bounce off each other, just like particles. But the fundamental reality isn't the collection of ripples, it's the lake itself. Now for the crucial leap. QFT says there isn't just one such field. There's a field for every single fundamental particle. There's an up quark field and a down quark field. Vibrations in these are the quarks inside your body's protons and neutrons. There's a photon field, and a ripple in this field is a particle of light, a photon. There's a gluon field, a neutrino field, a Higgs field, and on and on. Our universe is a symphony of these interlocking fields, all filling the entirety of space. What we think of as reality, the solid world of matter and energy, is just the fantastically complex dance of these underlying fields. When a particle is created, a field has gained a ripple of energy. When it's destroyed, a ripple has subsided, giving its energy back. Particles are no longer the fundamental actors. They are temporary manifestations of the fields, which are the true, enduring reality. The fields are the stage, and they're also the actors. They're all there is. This brings us back to the vacuum, to empty space. In this new picture, what does empty even mean? It can't mean the absence of everything, because the fields are always there, woven into the fabric of spacetime. You can't remove them. So, in quantum field theory, the vacuum is simply the state where all of these fields are in their lowest possible energy state. It's our cosmic lake when it's perfectly calm. No ripples. No particles. But here is where the quantum world delivers its most reality-bending twist. As it turns out, a quantum field can never be perfectly calm. It can never have an energy of exactly zero. There's a fundamental limit to how still this cosmic ocean can be. Even in its ground state, in the most perfect vacuum imaginable, the fields are seething with a minimum, non-zero amount of energy. And this constant, unavoidable energy of the void is what changes everything. It's what turns the quiet, empty stage of classical physics into a roaring, dynamic engine of creation. The architect's rules, how space decides. This new picture of reality gives us the framework to finally understand how space itself dictates the laws of existence. The properties of these fields, their built-in structures and energies, are the rules of the universe. They don't just allow things to exist, they actively define how they can exist. Let's start with mass. Why do some particles, like electrons and quarks, have mass, while others, like the photon, have none? Why isn't everything just zipping around at the speed of light? The answer lies in a very special field that permeates the entire universe, the Higgs field. You can think of the Higgs field as a kind of cosmic molasses, a thick, invisible syrup filling all of space. The photon field, for instance, glides right through it without any resistance. So its ripples, photons, are massless and travel at the speed of light. But other fields, like the electron field and the quark fields, have to interact with the Higgs field. When a ripple tries to move through one of these fields, it has to push its way through the Higgs molasses. This drag is what we perceive as mass. A particle that interacts strongly with the Higgs field, like the top quark, feels a lot of resistance and is very heavy. A particle that interacts weakly, like an electron, feels just a little resistance and has a small mass. Without the Higgs field, there would be no mass. No atoms, no planets, no people. Just a fleeting, chaotic soup. So here's our first stunning example. The structure of space, specifically the Higgs field, decides which particles get mass, and in doing so, allows our complex universe to exist. But that's just one part of the story. The truly mind-bending rule comes from a deeper quantum principle. As we mentioned, quantum fields can never be truly still. This is a direct consequence of one of the bedrocks of quantum mechanics, the Heisenberg uncertainty principle. In its most famous form, it says you can't know both the position and the momentum of a particle with perfect precision. But another version is even more profound. It relates energy and time. It says you cannot know the exact energy of a system over a very short time interval. There's always a fundamental fuzziness. What this means for the vacuum is revolutionary. Over extremely short timescales, the energy at any point in space can fluctuate wildly. The law of conservation of energy can be violated, as long as everything goes back to normal almost instantly. The universe allows energy to be borrowed from the vacuum, as long as it's repaid within a time frame set by the uncertainty principle. And what can this borrowed energy do? It can create particles out of absolutely nothing. For a fraction of a second, a packet of energy can erupt from the vacuum, creating a particle-antiparticle pair, like an electron and its antimatter twin, a positron. Then, an instant later, they must annihilate each other and vanish back into the nothingness they came from, repaying the energy debt. This isn't just a theory. This is happening everywhere, all the time. The vacuum of space, the emptiness between stars and between the atoms in your body, is a churning foam of these virtual particles, flashing in and out of existence too fast for us to see. This is the seething ocean we talked about. Up close, the calm lake is a chaotic, frothing frenzy. This is what physicists call quantum vacuum fluctuations. The vacuum is alive. It's a dynamic, energetic entity, constantly producing phantom particles. This is the true nature of empty space. It's not nothing. It's a place of infinite potential. We've journeyed from an empty box to a dynamic fabric, and now to a seething ocean of virtual particles. It's a fundamental shift in our understanding of reality. If you're finding this journey into the deep nature of the universe as fascinating as I do, consider subscribing to the channel. We have so much more to explore together. Evidence of the unseen, touching the void. This whole idea of a vacuum teeming with ghostly particles sounds like pure science fiction. How do we know it's real? The answer is that this empty space makes its presence known. Its seething energy has real, measurable effects. We can, in a very real sense, touch the void. The most famous evidence is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. The idea is elegant. Imagine you take two perfectly flat, uncharged metal plates and place them incredibly close to each other in a vacuum, just a few nanometers apart. Classically, nothing should happen. They should just sit there. But that's not what happens. A mysterious force actually pushes the plates together. Why? It's the quantum vacuum fluctuations. In the space outside the plates, virtual particles of all possible wavelengths are popping in and out of existence. But the tiny space between the plates acts like a resonance chamber. Only virtual particles whose wavelengths fit neatly into the gap can exist there. This means there's less vacuum energy between the plates than outside them. The pressure from the fluctuations in the outside world is greater than the pressure from inside the gap. This imbalance creates a net force, pushing the plates together. This isn't a subtle effect. It's been measured with high precision, and it matches the predictions of quantum field theory perfectly. The Casimir effect is tangible proof that the vacuum isn't empty. It has energy that can exert real force. Another piece of evidence comes from the heart of the atom itself. It's called the Lamb shift. According to earlier quantum theories, certain energy levels in a hydrogen atom should have been exactly identical. But in 1947, Willis Lamb discovered they weren't. There was a tiny, inexplicable difference. The explanation, it turned out, was the quantum vacuum. The electron orbiting the hydrogen nucleus isn't moving through a quiet void. It's moving through the frothing sea of virtual particles, and it's constantly being jostled and nudged by these fluctuations. This interaction slightly shifts the electron's energy levels, accounting for the tiny difference Lamb measured. The vacuum leaves its fingerprint on the atom itself. For decades, we could only see the asterisk effects of the vacuum, but that's been changing. While we can't take a literal picture of a virtual particle, recent experiments have gotten much closer to the source. In 2015, for instance, a team of scientists used incredibly short laser pulses and special crystals to directly measure the tiny, random variations in the electromagnetic field of the vacuum. They essentially caught a glimpse of the nothing of space as it momentarily fizzed into something, providing a more direct confirmation that the vacuum is indeed the seething, dynamic entity that QFT describes. The implications: we are also the void. So, what does this all mean? We started with space as an empty stage and have arrived at a universe where space is a dynamic, energetic substance, whose quantum rules dictate what can and cannot be. The implications are profound. It means the fundamental properties of our world, the mass of our particles, the stability of our atoms, the very forces holding the universe together, are not arbitrary. They are consequences of the underlying structure of the vacuum. The rules of existence are not written asterisk on space, they are written asterisk by space. The vacuum isn't a container for reality. It's the loom from which reality is woven. Think about it. The reason you have mass, the reason you are a solid object and not a flash of light, is because the fields that make you up are dragging their way through the Higgs field. The stability of your atoms depends on a delicate balance of forces, which themselves are being constantly shaped by the jittering of the quantum vacuum. We aren't separate from the void. We are a complex, persistent pattern of excitations within it. We are, in the most literal sense, a product of the structure of empty space. This idea dissolves the old boundary between thing and no thing. Everything we see, a star, a rock, a person, is a temporary, excited state of the vacuum. We are ripples on the surface of the quantum ocean. It connects us to the universe in the most intimate way imaginable. The laws that govern the particles in our bodies are the same laws inherent in the deepest voids between galaxies. The universe isn't a collection of separate objects in an empty box. It's a single, unified, interconnected entity. And perhaps most profoundly, it means that nothing is inherently unstable. A state of perfect, absolute nothingness cannot last. The laws of quantum mechanics forbid it. The universe seems to have a built-in bias towards existence. The ground state of reality is not emptiness. It is a state of boundless potential, eternally ready to bring forth something from nothing. The biggest mystery, the unsettled void. This beautiful, intricate picture of the vacuum is one of the crowning achievements of modern physics. It's tested and confirmed to an astonishing degree of accuracy. And yet, it has led us to the single biggest and most embarrassing mystery in all of science. It's a problem so massive it has a fittingly dramatic name: the cosmological constant problem, or the vacuum catastrophe. The problem is this. Using quantum field theory, we can calculate the amount of energy that should be in the vacuum from all those jittering quantum fields. When we do this, we get a number. It's a prediction. We can also observe the energy of the vacuum. One of the most shocking discoveries of the late 20th century was that the expansion of the universe is accelerating. It's being pushed apart by a mysterious repulsive force we call dark energy. Our best explanation for dark energy is that it is the energy of the vacuum itself. By measuring this cosmic acceleration, astronomers can figure out the actual, observed energy of empty space. Here's the catastrophe. When we compare the theoretical prediction with the observational measurement, they don't just disagree. They disagree on a scale that is impossible to even comprehend. The value predicted by our theory is about 10 to the power of 120 times larger than the value we actually observe. That's a 1 followed by 120 zeros. That discrepancy is greater than the number of atoms in the known universe. It is, without a doubt, the worst theoretical prediction in the history of physics. It tells us that while we have a powerful understanding of the vacuum, we are missing a gigantic piece of the puzzle. Why is the energy of the vacuum so fantastically smaller than our theory says it should be? If the vacuum energy were as large as the theory predicts, its repulsive force would be so immense it would have ripped the universe apart before galaxies, stars, or even atoms could ever form. The fact that we're here to even wonder about it means some unknown mechanism is canceling out almost all of that predicted energy, leaving just the tiny, delicate amount we observe. This is the frontier of physics. It's a mystery that ties the very small, the quantum fields, to the very large, the expansion of the cosmos. Solving it will likely require a completely new revolution in physics. Perhaps a theory of quantum gravity that finally unifies Einstein's and the quantum world. Conclusion. Our journey has taken us from the simple idea of an empty space to something far more majestic and strange. We've seen that space is not a static backdrop, but a dynamic stage that Einstein upgraded to a flexible fabric. Then, quantum mechanics transformed it once more into the ultimate reality. A set of fundamental fields whose properties write the rules of existence. The emptiness of space is an illusion. The vacuum is a churning ocean of virtual particles, a constant fizz of energy. This is a physical reality, its effects confirmed by experiments that let us feel the push of the void and see its influence on the very atoms we're made of. The structure of space gives particles their mass, and its restless energy is the foundation upon which our world is built. We are not just living in the universe, we are a manifestation of it. And yet, this profound understanding has led us to an even more profound mystery. The energy of this vacuum, the very thing that should define our cosmos, is a paradox, off by an amount so colossal it challenges the foundations of our theories. The next time you look up at the night sky, at the dark voids between the stars, remember what you're truly seeing. You are not looking at nothing. You are looking at the source code of reality. You are looking at an unresolved mystery, a seething ocean of potential that both governs our existence and defies our comprehension. Space isn't silent. It's whispering the laws of the cosmos, and we are only just beginning to learn how to listen. If this journey into the nature of reality sparked your curiosity, make sure you're subscribed and have notifications turned on. The universe is full of secrets, and we'll continue to explore them together. Thanks for watching. The impossible shapes banned by spacetime. On a blank sheet of paper, it is possible to draw a perfect triangle. Its three angles will add up to 180 degrees. Its sides are straight lines. We can define its form with an equation and hold its predictable shape in our minds. But the universe itself seems to have placed a ban on this shape. There appear to be cosmic laws, written into the fabric of reality, that make this simple, perfect triangle impossible to construct on a large scale. This isn't a thought experiment, but a fundamental rule of the reality we inhabit. The universe operates under a set of geometric laws far stranger than what we learn in school. These laws are not written on paper, they are woven into the cosmos by gravity. They bend and warp the stage upon which existence plays out and, in doing so, they determine what can and cannot exist. Today, we will explore these cosmic prohibitions. We will discover why some of the most basic shapes are outlawed by the universe, and how the geometry of spacetime itself acts as the ultimate gatekeeper of reality. The flat world we thought we knew. For most of human history, our understanding of space was, quite literally, flat. Not in the sense that the world was believed to be flat, but that the asterisk space it existed in was understood as a perfect, unchanging, three-dimensional grid. This is the world described by the ancient Greek mathematician Euclid, and it is a view that reigned in the human mind for over 2 millennia. Around 300 BC, in Alexandria, Euclid wrote his book, Elements, one of the most influential works in the history of human thought. In it, he laid down the fundamental axioms of geometry, intended as self-evident truths. Statements like, a straight line can be drawn between any 2 points. From a handful of these starting points, Euclid constructed an entire universe of shapes and logical certainty. At the heart of this system was a rule that seemed as solid as the others, the parallel postulate. It states that for a given straight line and a point not on that line, there is exactly one other straight line that can be drawn through that point that will never intersect the first. This rule defined the world. It's the reason the angles of a triangle sum to 180 degrees and why Pythagoras' theorem works for right-angled triangles. For architects and engineers, Euclidean geometry was the instruction manual for reality. This vision of a perfect, unchanging stage reached its peak with Sir Isaac Newton. In his universe, gravity was a force that acted across this Euclidean space. The action happened within the space, but the space itself did nothing. It was absolute and indifferent to the cosmic drama playing out within it. For 2,000 years, this picture was incredibly successful. Yet, a quiet intellectual question persisted around the fifth axiom, the parallel postulate. It made a claim about infinity, that certain lines would never meet. How could one be so sure? Mathematicians for centuries were convinced that the parallel postulate could be proven from the other, simpler rules. Men like Giovanni Sacchari in the 18th century devoted their lives to the task, only to falter, unable to accept the bizarre geometric worlds their logic was leading them to. They had stood at the precipice of a revolution, but turned back, convinced they had made a mistake. They had not made a mistake. They had discovered that the universe had more than one way to be. They had found the first hint that the perfect, flat, Euclidean world was not a certainty, but a choice made by the cosmos itself. The cosmic rebellion, when straight lines bend. The revolution began in the early 19th century when a handful of mathematicians, including Carl Friedrich Gauss, Janos Bolyai, and Nikolai Lobachevsky, decided to ask, what if the parallel postulate is false? This act of intellectual rebellion opened the door to 2 new, completely self-consistent geometric worlds. First, is the world of spherical, or elliptic, geometry, where there are no parallel lines. On the surface of a sphere, any 2 straight lines, or great circles, will always intersect. If you draw a large triangle on a globe, for instance, by starting at the North Pole, traveling to the equator, turning 90 degrees, walking a quarter of the way around the world, and then turning 90 degrees again to return to the pole, you will have drawn a triangle with three 90-degree angles. The sum of its angles is 270 degrees, not 180. The other possibility is hyperbolic geometry. This is the geometry of a surface that curves away from itself at every point, like a saddle. In this world, through a given point, you can draw infinitely many lines that will never intersect a given line. Here, the angles of any triangle always add up to less than 180 degrees. For decades, these non-Euclidean geometries were seen as mathematical curiosities. Then came Albert Einstein. He was wrestling with the nature of gravity, and his theory of general relativity, finalized in 1915, proposed a revolutionary idea. Gravity is not a force, but a consequence of the curvature of spacetime. Einstein unified space and time into a single four-dimensional fabric, spacetime. He showed that the presence of mass and energy warps this fabric. An object like the Earth, in orbit around the Sun, is not being pulled by a force. It is following the straightest possible path, a geodesic, through the four-dimensional spacetime that has been warped by the Sun's mass. Because spacetime itself is curved, that straight path appears to us as a nearly circular orbit. Gravity is geometry. Suddenly, non-Euclidean geometries were the language of the universe. The space around a star is curved. This brings us back to our impossible triangle. If we try to draw a triangle between three distant quasars, the lines of that triangle are beams of light. But these beams travel through a universe filled with matter and energy, following geodesics through curved spacetime. Because of this, when we add up the angles of this cosmic triangle, the sum will not be 180 degrees. While spacetime is approximately flat on smaller, local scales, allowing for nearly perfect Euclidean triangles, on a cosmic scale, a perfect Euclidean triangle with angles summing to exactly 180.000 degrees is made impossible by the universe's large-scale curvature. The ultimate prohibitions. Life near a black hole. Nowhere does geometry become more violent and twisted than near a black hole. A black hole is not an object, but a place, a region where spacetime has become so intensely curved that its geometry is fundamentally altered. Its most well-known feature is the event horizon, a purely geometric boundary. It is the point of no return because, inside it, the fabric of spacetime is curved to such an extreme that all possible paths, all geodesics, point only toward the center. Right now, you are being pulled inexorably in one direction through time, the future. Inside an event horizon, the direction toward the singularity, the black hole's center, becomes like the direction of future time. It is no longer a place you might go, it is your future. Trying to escape is like trying to travel back to yesterday. The geometry of existence forbids it. For a rotating black hole, the situation is even more complex. The black hole's rotation drags spacetime around it in a region called the ergosphere. Within this region, spacetime itself is dragged faster than the local speed of light relative to a distant observer. As a consequence, it is impossible to stand still. No matter how much force you apply, you will be swept along with the black hole's rotation. The very concept of a stationary object is banned by the geometry of this space. Even outside the event horizon, spacetime dictates what is possible. For a non-rotating black hole, there is an innermost stable circular orbit, ISCO, located at 3 times the Schwarzschild radius. The radius of the event horizon is 1 Schwarzschild radius. Any closer, and no stable orbit is possible. A small nudge will cause an object to spiral into the black hole. The simple shape of a stable circle is banned from this region. Closer still, at 1.5 times the Schwarzschild radius, is the photon sphere. Here, gravity is so strong that photons can be trapped in orbit. If you could stand on this sphere and look forward, light from the back of your head could circle the black hole and return to your eyes. We see direct evidence of these geometric rules through gravitational lensing. When light from a distant galaxy passes a massive object, its path is bent as it follows the curved geodesics. This can create multiple images of the same galaxy or distort it into arcs, a direct visual confirmation that gravity is shaping the paths of light across the cosmos. The bigger picture, higher dimensions and cosmic shape. The idea that geometry is an active participant in reality extends to the frontiers of theoretical physics. Theories like string theory propose that the universe has extra dimensions, perhaps 10 or 11, curled up into tiny, complex shapes at every point in space called Calabi-Yau manifolds. According to the theory, the precise geometry of these hidden dimensions determines the fundamental laws of physics. The vibrations of strings are constrained by this geometry, with each allowed vibration corresponding to a fundamental particle. The shape of these dimensions, therefore, may be what bans other hypothetical particles from existing. As for the shape of our universe as a whole, this remains one of the fundamental questions in cosmology. It can be flat, spherical, positively curved, or hyperbolic, negatively curved. By observing the cosmic microwave background, the afterglow of the Big Bang, cosmologists can search for signs of this large-scale curvature. Data from the Planck satellite, with its final results published in 2018, show that the universe is remarkably close to being flat, to within a 0.4% margin of error. This is the standard cosmological model. While there are some debated anomalies in the data that have led some to suggest a slight positive curvature, the consensus is that our universe is, for all intents and purposes, flat. This shape dictates the ultimate destiny of the cosmos. A flat or hyperbolic universe is expected to expand forever, while a spherical universe could potentially collapse back on itself. Geometry, it seems, holds the key to the beginning and the end of everything. Conclusion: we began with a simple triangle on a flat piece of paper, a symbol of a predictable world. We have since learned that the universe is not a sheet of paper. It is a dynamic, four-dimensional fabric, and the ink it is written in is gravity. This fabric is not a passive stage but an active participant. Its geometry, dictated by mass and energy, creates the rules. It tells planets how to move and light how to travel. It prohibits a perfect Euclidean triangle on a grand scale and forbids standing still near a rotating black hole. The universe is defined not just by what it contains, but also by what it disallows. These impossible shapes are a profound statement about the nature of reality. They show us that we are living by its geometric rules, following our own geodesics through a cosmos far stranger, and more complex, than a flat piece of paper could ever be. What concept from the strange geometry of our universe is most intriguing to you? The impossible triangle, the inability to stand still, or something else entirely? Let us know in the comments below. Distance is a lie, spacetime is a relationship. What's the distance between our Earth and the Moon? On average, it's about 384,000 kilometers of cold, silent nothing. A separation, a void, an absence. For almost all of human history, that's all it was. An uncrossable chasm. A reminder of how alone we are in the dark. But what if I told you that's a lie? A profoundly beautiful, cosmic lie. What if this nothing is actually the most powerful something in the universe? What if the separation between things isn't a passive void, but an asterisk active participant in reality? What if the distance between everything is actually a relationship? Today, we're going on a journey to dismantle your most basic intuitions about space, time, and the very fabric of existence. We'll see that the universe isn't a museum of lonely objects floating in an indifferent emptiness. Instead, it's a single, unified, dynamic entity, woven together by a fabric so strange and so powerful it dictates the fate of galaxies, the dance of planets, and the simple act of you sitting right there. This is the story of spacetime. And by the end, you will never look at the empty space between things the same way again. The old lie: space is an empty stage. To understand the revolution, we first have to understand the old way of thinking. For centuries, our vision of the cosmos was shaped by one of the greatest minds in history, Sir Isaac Newton. Newton gave us laws of motion and a law of universal gravitation that described the heavens with breathtaking precision for over 200 years. His entire framework was built on a simple, intuitive idea: absolute space and absolute time. Think of space as a gigantic, invisible, three-dimensional grid. A cosmic stage, infinite in all directions. This stage is absolute. It exists all on its own, whether there's anything in it or not. Time, in this world, was just as absolute, a single, universal clock, ticking at the same rate for everyone and everything, everywhere. On this rigid stage, with this universal clock setting the beat, the drama of the universe played out. Planets and stars were the actors, moving across the stage, pushed and pulled by forces. And the greatest of these forces was gravity. Newton's law of universal gravitation was a triumph. It says that every object with mass pulls on every other object. The more massive they are and the closer they are, the stronger the pull. It explained why an apple falls from a tree and why the moon orbits the Earth. It was perfect, except for one tiny, deeply unsettling problem that even bothered Newton himself. How did it work? Think about the sun and the Earth. According to Newton, the sun is constantly pulling on the Earth, keeping it in orbit. But how does the sun tell the Earth to move? How does that pull travel across 150 million kilometers of supposedly empty space? And here's the kicker. In Newton's model, this force works instantly. If the sun were to just vanish, poof, Newton's law implied the Earth would instantly fly off its path into the darkness. This concept, action at a distance, was like a ghost in the machine of Newton's otherwise perfect, clockwork universe. Even Newton found it absurd. He famously wrote that the idea of one body acting on another through a vacuum, with nothing to convey the action, was so absurd that no person with a competent faculty for thinking could ever fall for it. He knew a piece of the puzzle was missing, but he couldn't find it. He described what gravity did, but not how or why. This wasn't a minor detail. It was a huge crack in the foundation of physics. It hinted that our picture of space as a passive, empty stage was fundamentally wrong. For something to act instantaneously across a distance, the distance itself had to be doing something very strange. Or maybe, distance wasn't what we thought it was at all. The universe, it seemed, had a secret. And for 200 years, that secret stayed hidden, waiting for another revolutionary mind to uncover a truth far stranger than Newton could have ever imagined. The stage itself was about to become the main actor. The first revelation, the speed limit of reality. The end of the 19th century brought a new mystery, one that would finally shatter Newton's universe. And it didn't come from the grand motion of planets, but from the behavior of the most ethereal thing we know: light. For decades, physicists had been studying light, and James Clerk Maxwell discovered that it was an electromagnetic wave. His equations even predicted its speed, about 300,000 kilometers per second. But this raised a critical question: speed relative to what? In our everyday world, speeds are relative. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the ground sees the ball moving at 120 kilometers per hour. Speeds add up. It's common sense. So, physicists assumed the same was true for light. They imagined all of space was filled with an invisible substance called the luminiferous ether, the medium light waves traveled through. It stood to reason that the speed of light should change depending on how the Earth was moving through this ether. In 1887, Two American scientists, Albert Michelson and Edward Morley, set out to measure this change. They built an ingenious experiment to detect the ether wind created by Earth's orbit around the Sun. They split a beam of light, sent the two halves in different directions, and then brought them back together. Any difference in speed would create a telltale pattern. They ran the experiment. They checked their results. They ran it again and again. The result was always the same: nothing. There was no difference. The speed of light was stubbornly, inexplicably, constant. This was a catastrophe for physics. It was like throwing a ball forward on a train and having someone on the ground see it moving at the exact same speed you do. It broke all the rules. It took nearly 2 decades for someone to truly grasp what this meant. In 1905, a young patent clerk in Bern, Switzerland named Albert Einstein, published a paper that changed everything. He started by simply accepting the result. What if, he asked, this isn't a paradox? What if the speed of light in a vacuum being the same for all observers is a fundamental law of the universe? From this one bold idea, Einstein was forced to a conclusion that defied all common sense. If the speed of light is absolute, then space and time cannot be. To make reality consistent, they had to be flexible. They must stretch and shrink depending on your motion. This is the core of Einstein's special theory of relativity. An observer watching a fast-moving spaceship would see its clocks ticking slower, that's time dilation. They'd also see the spaceship itself as being squashed in its direction of motion, length contraction. And from the perspective of someone on the spaceship, everything would seem normal, but they'd see the outside observer's time as slow and length as contracted. This isn't a trick of perception. It's a genuine feature of reality. Time and space are not the rigid, absolute things Newton thought they were. They are relative. A few years later, one of Einstein's former professors, Hermann Minkowski, realized what this truly meant. The reason space and time were acting so strangely was because they weren't separate things at all. They are two parts of a single, unified, four-dimensional structure. He famously declared, henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He called this union spacetime. Think of it this way. If you and a friend are in a room, you might disagree on how far an object is, forward, versus, to the left, depending on where you're standing. Your coordinates are relative, but you'd both agree on the direct, diagonal distance to that object. Minkowski showed that something similar happens with space and time. Different observers, moving relative to each other, will slice up this 4D reality into space and time in different ways. They'll disagree on the time between two events and the distance between them. But they will always agree on a special, combined, distance, called the spacetime interval. This means we aren't just moving through space. We are always traveling through spacetime. In fact, we are all moving through spacetime at a single, constant speed, the speed of light. When you're standing still, all of that motion is through the time dimension. But as you start to move through space, some of that motion through time gets diverted. That's why time slows down for a moving object. You're trading motion through time for motion through space to keep your total speed through spacetime constant. This was a staggering revelation. Newton's passive stage was gone, replaced by a dynamic, four-dimensional block. But this was only half the revolution. Spacetime explained the mystery of light, but it hadn't solved Newton's old problem, the ghostly action at a distance. What was gravity in this new picture? Einstein knew his work wasn't done. The greatest revelation was still to come. The grand revelation, spacetime as the relationship. After 1905, Einstein was celebrated, but he was also deeply unsatisfied. His theory of special relativity was beautiful, but it had a glaring hole: gravity. Worse, it made Newton's gravity even more of a problem. If nothing can travel faster than light, then Newton's instantaneous force was flat out impossible. If the sun vanished, there had to be a delay before the Earth knew about it. Gravity needed time to travel. But how? For 10 years, Einstein wrestled with this. The breakthrough came in what he called his happiest thought. He imagined a man falling from a roof. He realized that while falling, the man wouldn't feel his own weight. If he dropped objects from his pockets, they'd float beside him. In his own little bubble of existence, gravity would have disappeared. This led Einstein to a profound idea he called the asterisk principle of equivalence asterisk. The effects of gravity are completely indistinguishable from the effects of acceleration. If you woke up in a sealed box, you couldn't tell if you were sitting on Earth, being pulled down by gravity, or in a rocket ship in deep space, accelerating up at 9.8 meters per second squared. This was the key. Gravity and acceleration were two sides of the same coin. And if acceleration could warp space and time, then so could gravity. Imagine that accelerating rocket. If you shine a flashlight across the room, what happens? As the light travels, the rocket accelerates upwards. By the time the light hits the far wall, the floor has moved up. To the person inside, the light beam would look like it bent downwards. And because of the equivalence principle, if it happens with acceleration, it must happen with gravity. Light itself must bend when it passes a massive object. This was the final piece of the puzzle. The reason light bends isn't because a force is pulling it. The reason planets orbit suns is not because a force is pulling them. It's because mass and energy fundamentally change the geometry of the universe. They warp the very fabric of spacetime. This is the core of Einstein's general theory of relativity, his 1915 masterpiece. Gravity is not a force. Gravity is the curvature of spacetime. The classic analogy is a trampoline. If you place a heavy bowling ball, the sun, in the center, it creates a deep curve. Now, roll a marble, the Earth, nearby. It won't travel in a straight line. It will follow the curve in the sheet, rolling around the bowling ball in what we see as an orbit. The marble isn't being pulled by the ball. There's no invisible strain. The marble is simply following the straightest possible path, a geodesic, through a curved surface. And that is the revolutionary truth. The Earth isn't being pulled by the sun. The Earth is simply following the straightest possible path through the curved spacetime created by the sun's mass. The physicist John Archibald Wheeler summed it up beautifully. Spacetime tells matter how to move. Matter tells spacetime how to curve. This is the relationship. The distance between the sun and Earth isn't a passive void. It's an active, dynamic, curved geometry that is constantly telling the Earth how to move. Of course, this isn't just space that's curved, time is curved too. This is called gravitational time dilation. A clock closer to a massive object, where gravity is stronger, actually ticks slower than a clock farther away. This isn't a theory. It's real, and your phone proves it every day. The GPS in your phone relies on satellites, each with an incredibly precise clock. These satellites are in a region where Earth's gravity is weaker, so general relativity predicts their clocks should run slightly faster than clocks on the ground. They are also moving very fast, so special relativity predicts their clocks should run slightly slower. When you combine the effects, the satellite clocks gain about 38 microseconds every day. It sounds tiny, but if engineers didn't correct for this curvature of spacetime, your GPS would be off by about 10 kilometers every single day asterisk, making it useless. The fact that you can navigate to a coffee shop is daily proof that spacetime is a real, physical thing that can be curved. And the proof doesn't stop there. In 1919, Sir Arthur Eddington saw starlight bending around the sun during an eclipse, just as Einstein predicted. And on September 14, 2015, the LIGO experiment made history. For the first time, we directly detected gravitational waves, ripples in the fabric of spacetime itself, created by two black holes colliding over 1 billion light-years away. These weren't particles traveling through space, they were waves of spacetime, stretching and squeezing everything as they passed. It was the ultimate confirmation. Spacetime isn't the stage, it's the story. We've replaced the old lie of an empty void with the profound truth of a dynamic, curving fabric. The nothing between worlds is actually the something that governs their dance. But this raises an even deeper question. If the universe is governed by the shape of spacetime, what does that mean for distance itself? What does it even mean to be somewhere? The rabbit hole goes even deeper. Before we take that final plunge, if you're enjoying this journey, consider subscribing so you don't miss our future explorations. Now, let's redefine reality one more time. The deeper dive: distance is a lie. So, what is distance? It's not a simple ruler measurement in a static grid. An orbit is actually a straight line through curved 4D spacetime. The distance we see is just a shadow of a more fundamental reality: the spacetime interval, a quantity all observers can agree on. This is already a huge leap from our intuition. But some physicists and philosophers argue we need to go even further. They suggest that even Einstein's revolution still assumed that spacetime was a fundamental thing that existed on its own. But what if it doesn't? What if spacetime itself is not fundamental, but emergent? This is a return to an old debate between Isaac Newton and his rival, Gottfried Wilhelm Leibniz. Newton believed space was a real, existing container. Leibniz was a relationalist. He argued that space is nothing but the collection of relationships between objects. Leibniz's argument is clever. Imagine shifting the entire universe 3 feet to the left. What would change? Nothing. Every object would still be in the same position relative to every other object. Leibniz argued that if there's no observable difference, then it's the same scenario. Therefore, the idea of the universe existing in a specific location is meaningless. All that really exists is the network of relationships. Space is just the language we use to describe them. For centuries, Newton's view won, mostly because of his rotating bucket experiment. If you spin a bucket of water, at first the water stays flat. Then, it starts spinning with the bucket, and its surface becomes concave. The key moment is when the water and bucket spin together. There's no relative motion between them, yet the water's surface is curved. Newton said this proved the water was rotating relative to something absolute, space itself. Leibniz didn't have a good answer. But much later, the physicist Ernst Mach suggested the water curves not because it's rotating relative to absolute space, but because it's rotating relative to the average mass of all the other stuff in the universe, the distant stars. In a totally empty universe, Mach argued, rotation would be meaningless. Einstein was hugely inspired by Mach's principle. In many ways, general relativity is a deeply relational theory. The distribution of matter and energy defines the geometry of spacetime. However, it's not perfectly relational. Einstein's equations allow for things like gravitational waves in an otherwise empty universe, which suggests spacetime can have a life of its own. This has led modern physicists to push the relational idea to its limit. Thinkers like Carlo Rovelli propose a view called relational quantum mechanics. Here, an object's properties are only defined when it interacts with another system. Things don't have properties in isolation, only relative to something else. The universe becomes a vast, intricate network of these interactions. Even more ambitious are ideas like the Wolfram Physics Project, which explores whether the universe could be, at rock bottom, a simple rule generating a massive, evolving network of abstract relations, a hypergraph. In this model, everything we know, space, time, particles, the laws of physics, are emergent properties of this network structure. Space is literally the web of connections between the fundamental atoms of existence. In this view, distance isn't just a asterisk description of a relationship, distance is the relationship. Two particles are far apart because there's a huge number of connections in the network you have to cross to get from one to the other. You can't just instantly appear on the moon because the very structure of the network that is reality forbids it. And this brings us back to the most basic experience of all: touch. When your finger touches a table, what's happening? It's the electromagnetic fields of your atoms repelling the fields in the table. But those fields operate according to the rules of physics. And in this deepest view, those rules are the structure of the spacetime network. The distance between your finger and the table has shrunk to the point where the fundamental relationships that define them as separate things start to interact. A touch isn't a violation of separation, but the most intimate expression of a relationship, governed by the fabric of reality itself. Conclusion: the grander vision. We started with a simple question: what is the distance between the Earth and the Moon? We thought of it as a void. We've journeyed from that simple lie to a truth of staggering beauty. We saw how Newton's absolute stage was cracked by his ghostly action at a distance, then shattered by the stubborn constancy of light. This led us to the first great revelation: the union of space and time into a single 4D fabric, spacetime. Then, guided by his happiest thought, Einstein revealed something even grander. Gravity isn't a force pulling us through the void. Gravity is the shape of the void. Mass and energy curve spacetime, and everything simply follows the straightest possible path through that curved geometry. Your phone's GPS proves this every day. The echoes of colliding black holes, heard by LIGO, are the sounds of this fabric vibrating across the cosmos. And finally, we peered over the edge into an even deeper reality, where spacetime itself might not be fundamental. Where, at the very bottom, there may only be a network of interactions, from which space, time, and everything we know emerges. In this view, the universe is not a collection of things in space. The universe is the network of relationships, and space is just what that network looks like. So, is distance a lie? It's a lie if you think of it as a simple separation, an absence, a nothingness. Distance is a relationship. It is the language of space-time, the grammar of the cosmos. Every orbit, every collision, every star burning in the night sky is a conversation happening in the geometry of reality. The universe isn't a collection of lonely objects separated by an uncaring void. It is a single, profoundly interconnected entity. We are not just in the universe. We are a part of its unfolding geometric story. The fabric that separates the stars is the same fabric that binds our atoms and allows us to relate to everything and everyone else. Why some patterns are impossible to create? There is a quiet law woven into the fabric of space, a hidden truth about the nature of patterns. It suggests that in any system, if it becomes large enough, certain forms of order are not just possible, but inevitable. It suggests that complete and utter chaos, it turns out, cannot truly exist. To see a glimpse of this, we can begin with a simple thought experiment. Imagine a grid of dots, like a quiet, empty checkerboard. We can start placing markers on the intersections, with only one rule to follow. No three markers can ever form a straight line, in any direction at all. At first, the process feels simple, almost like a game. The first few markers are placed with ease. We feel a sense of cleverness, dodging and weaving through the empty space. But as we continue, something strange begins to happen. The board feels as if it's shrinking. The open spaces, once plentiful, become precarious. Each new spot we choose seems to threaten a new, forbidden alignment with two other markers already on the board. We might find ourselves backtracking, rearranging, puzzling over a simple game of dots. And then, no matter how carefully we proceed, we arrive at a point where we can go no further. This isn't a failure of strategy, or a sign that we've missed some simple trick. It's a demonstration of a hidden principle. It's a look into a world of what mathematicians call forbidden configurations, patterns that are not just difficult to create, but impossible to avoid. What we've just explored is a famous puzzle in combinatorial geometry, often called the no 3-inline problem. It has the feeling of a game of skill, but it is actually a cage. The rules of this cage aren't written on the board. They are woven into the very fabric of geometry. As more and more dots are added, we are not just filling a space, we are building a system. And with every piece we add, the system becomes more constrained, the geometric pressure builds, until it is forced to take on a shape we were trying to avoid. The line of 3 dots is a forbidden pattern. And the surprising truth is that the world is full of them, patterns that are impossible to create, precisely because some other pattern is impossible to avoid. Today, we're going on a journey from a simple dot puzzle to a profound mathematical principle that governs everything from the structure of our social networks to the design of computer chips. We are going to explore why some patterns are simply impossible. Let's return to our grid. The no 3-inline problem was first shared widely by the great English puzzle maker Henry Houdini around the year 1900. Houdini, a man who could turn almost anything into a brain teaser, presented it as a challenge involving pawns on a chessboard. He was a master of what we might call recreational mathematics, but in this simple setup, he had stumbled upon something that has kept mathematicians occupied for more than a century. Let's explore the game for a moment. On a tiny 3x3 grid, like a tic-tac-toe board, there are 9 total spots. We can place 1 dot, 2, 3, 4, 5, but when we attempt to place the 6th, we will always, inevitably, create a line of 3. There is no way around it. The maximum for a 3x3 grid is 6. This has been proven. This leads to a natural inquiry. For any n by n grid, there must be a maximum number of dots. A number now known as the no 3-inline number for a grid of size n. A simple observation gives us a kind of theoretical speed limit. In any given row or column, we can't place more than 2 dots. A third would instantly create a line. So, for an n by n grid, the absolute maximum number of dots one could ever hope to place is 2 times n. For our 3x3 grid, 2 times 3 is 6. We reached the maximum. For a 4x4 grid, the theoretical maximum is 8, and with a bit of exploration, one can find ways to place 8 dots without any 3 forming a line. This pattern appears to hold. For a 5x5 grid, one can place 10 dots. For a 10x10 grid, 20. In fact, for every grid size n that has been checked up to 60, mathematicians and computer scientists, using clever algorithms, have found a way to place exactly 2 n dots. And so, a conjecture was born. Perhaps the answer is always 2n. But this is where the mystery deepens. No one has been able to prove it. For all we know, there might be some enormous grid size, perhaps a billion by a billion, where the geometric pressure becomes so immense that it's no longer possible to place 2 n dots. The difficulty is that the number of potential lines you have to check for explodes as the grid gets larger. We aren't just checking rows and columns. We're checking all the diagonals, and not just the main diagonals, but a ghost-like web of every possible straight line. A line can have a slope of 1/2, or 3/5, or -7/12. Any 3 points, anywhere on that vast grid, that happen to fall on a single straight line, means the rule has been broken. The complexity is staggering. This is the kind of problem that falls into a class known for being computationally intensive, meaning that even for our fastest computers, finding the absolute maximum for a large grid is practically impossible. The computer can't use some clever mathematical shortcut. It often has to resort to a brute force search through an astronomical number of combinations. So we have this simple puzzle, born from the mind of a recreational puzzler, that leads us to the absolute frontiers of computation. And it leaves us with a quiet question. Why does it become so hard? Why does the space itself seem to fight back? What if the real story is that as a system grows, it must create certain kinds of order? To understand this, we need to step away from the grid for a moment and look at an even more surprising, and perhaps more beautiful, problem. The story of our next problem begins not with a puzzle, but with a conversation among friends in Budapest, Hungary, during the winter of 1933. A young mathematics student named Esther Klein was meeting with a group of friends, including two brilliant young thinkers, George Szekeres and Paul Erdős. Klein, who would go on to be a respected mathematician, shared a curious geometric observation she had made. Here is what she proposed. Take a blank sheet of paper and place 5 points on it. The only rule is that they must be in what mathematicians call general position, which simply means no three of them can form a straight line, the very rule from our last puzzle. Klein's observation was this: no matter where you place those 5 points, you will always be able to find a subset of 4 of them that form the vertices of a convex quadrilateral. Let's explore what this means. A quadrilateral is just a 4-sided shape. A asterisk convex one is a shape where all its interior angles are less than 180 degrees, like a well-behaved rectangle or kite. Its opposite is a concave quadrilateral, which looks as if it has a dent or a caved inside. Klein's assertion was that no matter how you arrange 5 points, you can never avoid creating a convex one. This seems almost magical. You can try to imagine it. If you scatter 5 dots in a circle, any 4 of them form a convex quadrilateral. If you place 4 in a tight square and the 5th far away, the 4 in the square still work. But what if we try to be tricky? What if we place 3 points to form a triangle, and then place the other 2 points inside that triangle? This tricky case holds the key. We have a large triangle made of 3 points, with 2 more points inside. Now, if we imagine the line formed by those 2 inner points and extend it indefinitely, this new line cannot hit any of the 3 vertices of the outer triangle, because we said no 3 points can be on a line. Therefore, it must pass through 2 of the sides of that outer triangle. This means that on one side of our new line, there will be 1 vertex of the big triangle, and on the other side, there will be 2. And in that arrangement, the shape is revealed. If we take the 2 interior points, and the 2 vertices of the outer triangle that are on the same side of the line we drew, those 4 points form a convex quadrilateral. It cannot be escaped. The group of mathematicians in Budapest was captivated. This was a property of space itself. Paul Erdős, a man who would become one of the most prolific mathematicians of the 20th century, found this result so beautiful and its story so charming that he nicknamed it the happy ending problem. The name stuck, not just for the delight of the mathematics, but because the intellectual collaboration between Esther Klein and George Szekeres blossomed into romance, and they were married in 1937. But the story doesn't end there. The group immediately wondered, what's next? Klein had shown that 5 points guarantee a convex quadrilateral, a 4-sided polygon. How many points are needed to guarantee a convex pentagon, a 5-sided polygon? They worked on it, and Szekeres and Erdős were able to prove that you need 9 points. With 8 points, it's possible to create an arrangement with no convex pentagon, but the moment a 9th point is added, one is forced into existence. The question naturally generalizes. For any number n, what is the minimum number of points required to guarantee a convex n-sided polygon? We know the number is 3 for a triangle, 5 for a quadrilateral, and 9 for a pentagon. In 2006, it was shown to be 17 for a hexagon. Beyond that, we enter the realm of the unknown. Erdős and Szekeres conjectured that the formula is 2n2 plus 1. This simple formula works for all the values we know. If true, it would mean that to guarantee a 10-sided decagon, you'd need 257 points. The numbers grow incredibly fast. Proving or disproving this has been one of the great open problems in the field for almost a century. These 2 stories, one of a pattern we try to escape, and one of a pattern we cannot avoid, seem different. But they are both whispers of a much deeper principle, an idea that in any sufficiently large system, a kind of order is not just likely, it is inevitable. This idea has a name. Ramsey theory. Ramsey theory is, at its heart, the formal study of the principle that complete disorder is an illusion. Given a large enough structure, no matter how chaotic it appears, you are guaranteed to find within it a smaller, highly ordered substructure. The idea is often captured in a simple, intuitive story known as the party problem. It goes like this. At any party, any two people are either mutual friends or mutual strangers. The question is, what is the minimum number of guests you must invite to guarantee that there will be either a group of 3 mutual friends, or a group of 3 mutual strangers? With 3, 4, or even 5 people, you can't be certain. But the surprising answer is 6. With 6 people at a party, there is a 100% guarantee that you will find a clique of 3 mutual friends or 3 mutual strangers. The reasoning is surprisingly elegant. Pick any person at the party, let's call her Alice. She has a relationship with the other 5 guests. Each is either a friend or a stranger. This is where a classic mathematical tool called the pigeonhole principle comes in. If you have 5 pigeons, the guests, to put into 2 pigeonholes, friends of Alice or strangers to Alice. One of those holes must contain at least 3 pigeons. So, Alice has at least 3 friends or at least 3 strangers among the guests. Let's take the first case. Alice has at least 3 friends, we'll call them Bob, Charlie, and David. Now, we look at them. If any 2 of them are friends, say, Bob and Charlie, then we have found our group of 3 mutual friends, Alice, Bob, and Charlie. We're done. But what if none of them are friends? If Bob, Charlie, and David are all mutual strangers, then we have found our group of 3 mutual strangers. Again, we're done. In every scenario, we are forced into a corner. We cannot construct a social network of 6 people that avoids both a triangle of friends and a triangle of strangers. The structure is inevitable. This number, 6, is called a Ramsey number, R3. It's the essence of Ramsey theory. We are coloring a structure, the relationships between people, and discovering that if the structure is large enough, we can't avoid creating a monochromatic, or single-colored, substructure. Now we can see how this connects back to our dots. In the happy ending problem, we have a set of points. The structure is the collection of all possible quadrilaterals, which we can color as either convex or concave. Esther Klein proved that any set of 5 points must contain a convex one. This is a Ramsey-like result. And for the no 3 inline problem, the spirit is the same. As the density of points on the grid increases, the emergence of ordered substructures, like lines, becomes more and more likely. You are building a system so constrained that it is forced to produce the very pattern you're forbidding. Ramsey numbers for larger structures are notoriously difficult to calculate. We know R3 equals 6. R4 which guarantees 4 mutual friends or strangers, is 18. As for R5, we only know it's somewhere between 43 and 48. The exact number remains unknown. Paul Erdős once said that if aliens demanded the value of R5, or they would destroy the planet, we should marshal all our computers and try to find it. But if they asked for R6, he said, we should marshal all our armies and attack them first, because the computation would be utterly beyond us. This difficulty shows just how deeply these inevitable patterns are hidden. They are not obvious. They are emergent properties of large systems. This principle, that complete disorder is a kind of illusion, echoes far beyond pure mathematics. It's a concept with reflections across science and technology. In telecommunication networks, for example, which are really just giant graphs of nodes and connections, Ramsey theory can help prove that any sufficiently large network is guaranteed to have certain robust sub-networks, or certain types of bottlenecks. You don't waste time trying to design an architecture that avoids a certain type of clustering if mathematics tells you that avoidance is impossible beyond a certain scale. Instead, you design the system to handle that inevitable structure. But perhaps the most profound implication is more philosophical. Ramsey theory is a quiet rebuttal to the idea that the universe is fundamentally random. It tells us that structure is an inherent property of scale. If you have enough stuff, points, people, numbers, or stars, and enough relationships between them, ordered patterns will necessarily emerge. A single water molecule is simple, but put enough of them together and lower the temperature, and they don't just form a chaotic slush. They are forced into a highly ordered crystalline structure, a snowflake. The intricate, six-fold symmetry of a snowflake is, in a way, an inevitable pattern emerging from the constraints of molecular bonds and energy states. When we look at a complex system, a biological ecosystem, a social network, or the distribution of galaxies in the cosmos, and we see a pattern, our first instinct is to look for a cause. We might assume some force or designer imposed that order. Ramsey theory offers a startling alternative. Perhaps the pattern exists simply because the system is large enough and complex enough that the asterisk absence of such a pattern would be a mathematical impossibility. The order isn't necessarily a sign of design, it can be a sign of inevitability. This shifts our perspective. We move from asking, "What created this pattern?" to a new, more profound question. What are the underlying rules of this system that make this pattern unavoidable? The journey from a simple dot game to a universal principle of order shows how mathematics can reveal these hidden truths about the world. If this kind of calm exploration into the quiet, deep connections of our world unwinds you, consider subscribing to the channel. There are countless other puzzles and principles out there, each one a thread in the grand tapestry of knowledge. We started with a simple challenge on a grid, and saw how it leads to bewildering complexity. We then saw, with the happy ending problem, how the opposite can be true. That some patterns are not hard to find, but impossible to miss. The bridge between these two worlds is Ramsey theory. It reframes the entire quest. The real story is the tension between chaos and order. And Ramsey's theorem is the mathematical guarantee that in this cosmic tug-of-war, as systems grow, order always wins. The principle is solid even when the particulars are shrouded in mystery. The forbidden configuration of a world with no three in a line on a sufficiently dense grid, or a party of six with no clique of friends or strangers, is not a world we can build. It's a mathematical fiction. These patterns are impossible to create because the universe seems to have a fundamental bias toward structure. Space itself, it seems, abhors a vacuum of pattern. So, the next time you see a pattern in the world, in the flocking of birds, the structure of a conversation, or the arrangement of stars in the night sky, you can ask yourself, is it there by design, or was it simply impossible for it not to be? Why getting bigger is a death sentence. A thought experiment. If a person were to wake up tomorrow at 10 times their normal height, the result would not be superhuman ability. Instead, it would be immediate, catastrophic structural failure. This outcome is not a fantasy, but a consequence of a fundamental physical principle that links geometry to existence. This principle is governed by the mathematics of squares and cubes. It is a rule that applies to organisms, to architecture, and to celestial bodies, and it is the reason why the concept of a giant, as commonly imagined, is a physical impossibility. This law acts as a silent constraint on the universe, dictating the potential shapes of life and the limits of physical structures. Today, we will examine this principle. We will explore what happens when objects are scaled up to the point of failure, and scaled down to where the laws of physics themselves appear to change. By the end, you will not only understand why a simple increase in size can lead to collapse, but you will also see the influence of this law across many aspects of the physical world. The mathematics of scaling. To understand this universal limit on size, we can begin with a simple geometric shape. Consider a cube, 1 centimeter on each side. Its surface area, the total area of all its faces, is 6 square centimeters. This is the portion of the cube that interacts with its environment. Its volume, the space it occupies, is 1 cubic centimeter. This represents its mass. The ratio of its surface area to its volume is 6 to 1. If we double its linear dimensions to 2 centimeters per side, its properties change disproportionately. The surface area of each face becomes 4 square centimeters, for a total surface area of 24 square centimeters, an increase by a factor of 4. The volume, however, becomes 8 cubic centimeters, an increase by a factor of 8. The surface area has scaled with the square of the multiplier, 2 to the power of 2 equals 4, while the volume has scaled with the cube, 2 to the power of 3 equals 8. The ratio of surface area to volume has now decreased from 6 to 1 to 3 to 1. If we scale the cube to be 10 times larger, each side is now 10 centimeters. Its surface area is 10 times 10, multiplied by 6 faces, for a total of 600 square centimeters, a 100-fold increase. Its volume, however, is 10 times 10 times 10, which is 1,000 cubic centimeters, a 1,000-fold increase. An object that is 10 times taller has become 1,000 times heavier. The surface area to volume ratio has fallen to 0.61. This is the square cube law. As an object increases in size, its volume consistently grows faster than its surface area. This is a geometric certainty. It was the Italian astronomer and physicist Galileo Galilei who first formally described this principle in 1638 in his work, Dialogues Concerning Two New Sciences. Galileo noted that nature could not simply scale its creations linearly. He wrote about the structural limits of ships, buildings, and the bones of animals. He understood that a very large animal could not have the same proportions as a smaller one. Its bones would need to be disproportionately thicker to support their amplified weight. This has direct physical implications. For a living organism, surface area relates to the strength of a bone's cross-section, the skin's ability to radiate heat, and the lung's capacity to absorb oxygen. Volume relates to mass, the heat generated by cells, and the body's total demand for oxygen. The square cube law creates a critical imbalance. As an organism grows, its needs, which are tied to volume, increase by a power of 3. Its ability to meet those needs, tied to surface area, increases by only a power of 2. This is not just a problem, it is a cascading, multi-system failure waiting to happen. It is the physical basis for the limits on an organism's size. The physiological consequences of scaling. Let's return to the hypothetical human, 10 times their normal height. Their first physical challenge would be structural integrity. First, consider the skeletal system. The strength of a bone like the femur is determined by its cross-sectional area, a two-dimensional property. Weight, however, is a product of volume, a three-dimensional property. By becoming 10 times taller, the bone's cross-sectional area increases by a factor of 100. They are 100 times stronger. But the body's volume, and therefore its mass, has increased by a factor of 1,000. Each square inch of the scaled-up bones must now support 10 times more weight. A human femur can withstand about 10 to 12 times the body's static weight, a safety margin that allows for activities like running and jumping. For our scaled-up human, simply standing still would remove this safety margin entirely. The compressive stress would exceed the material limits of bone, and the skeletal structure would fail. The tallest man in recorded history, Robert Wadlow, who stood just under 9 feet tall, required leg braces to walk and had limited sensation in his feet. His height was a clear illustration of the physical challenges imposed by the square cube law. Let's assume the skeletal problem is solved with an impossibly strong material. The next challenge is thermoregulation. Every cell in the body generates heat through metabolism. The total heat produced is proportional to the body's volume. This heat must be dissipated into the environment, a process that occurs primarily through the skin, a surface. The result is a 1,000-fold increase in heat generation, but only a 100-fold increase in the surface area available for cooling. The ratio of heat production to heat dissipation becomes 10 times less favorable. The core body temperature would rise uncontrollably, leading to hyperthermia. An elephant-sized mouse, if it could exist, would face the same thermal problem. If this were also solved through some external mechanism, the next failure point would be the respiratory system. The need for oxygen is determined by the metabolic demands of the entire body's volume. The ability to acquire oxygen is determined by the surface area of the alveoli in the lungs. A 1,000-fold demand for oxygen would be met with only a 100-fold supply. This would lead to a state of permanent hypoxia, where tissues are starved of oxygen. Even if respiration were solved, a similar problem would arise with digestion. A body 1,000 times larger requires 1,000 times the nutrients. However, the intestines absorb these nutrients through their inner surface, which has only grown by a factor of 100. This would lead to chronic malnutrition, as the body could not absorb energy fast enough to sustain its mass. Finally, the cardiovascular system would fail. The heart is a muscle whose strength is proportional to its cross-sectional area. It would need to pump blood to a brain located many feet higher, requiring immense pressure. The blood vessels, whose wall strength scales with area, would be unable to withstand this pressure. The heart muscle itself, now 100 times stronger, would be tasked with servicing a system 1,000 times larger. The physical demands would lead to heart failure. There are no simple loopholes. Each biological system is constrained by these geometric and physical realities. Evolutionary solutions and inherent limits. This thought experiment illustrates a principle that has shaped the evolution of all life. Every organism is either small enough to be unaffected by the harshest constraints of the square-cube law, or it has evolved specific adaptations to manage them. The elephant is a clear example of this adaptation. It does not resemble a scaled-up mouse because such a form would collapse. Its legs are thick, columnar structures positioned vertically under its body, an architectural solution to support its immense mass. The cross-sectional area of its bones has been maximized to handle a weight that increased by the cube. This is the law expressed in skeletal form. For thermoregulation, an elephant's large, thin ears function as radiators. They are filled with blood vessels and dramatically increase the animal's total surface area to help it dissipate metabolic heat. Conversely, consider the ant. An ant can carry many times its own body weight. At this small scale, the influence of its own mass, a function of volume, is minimal. The dominant forces are related to muscle strength, which is proportional to cross-sectional area. The ratio of its strength to its weight is therefore very high. If an ant were scaled up to the size of an elephant, this advantage would vanish. Its strength would increase by the square, but its weight would increase by the cube. Gravity, once a minor factor, would become the dominant force, and its structure would collapse. One primary way for an organism to achieve massive size is to leave the land. The blue whale is the most massive animal known to have ever existed, weighing up to 200 tons. It manages this by using the buoyancy of water to support its weight. This counteracts the force of gravity, relieving the immense strain on its skeleton. If placed on land, a blue whale's own mass would crush its internal organs. It survives because it exists in an environment that negates the primary consequence of its size. The law also imposes firm limits. For instance, insects do not reach the size of dogs. This is not due to their exoskeletons but to their respiratory system. Insects breathe through a network of small tubes called tracheae, which deliver oxygen directly to tissues via diffusion. This system is efficient for small bodies where diffusion distances are short. As an insect's size increases, its volume and oxygen demand grow by the cube. The tracheal system's ability to deliver oxygen cannot keep pace. To supply a large body, the network of tubes would have to be so extensive that it would leave no room for internal organs. The very system that allows them to breathe also sets a hard limit on their maximum size. Every living being represents a compromise, a negotiation with the mathematics of the universe. Beyond biology, structures, forces, and the quantum scale, the square-cube law is not limited to biology. It is a fundamental principle of physics that extends to man-made structures and the cosmos itself. In engineering, one cannot build a skyscraper by simply scaling up the blueprints for a house. This is due to what is known as the size effect on strength. For many materials, a larger volume is statistically more likely to contain a microscopic flaw, such as a crack or an air bubble. Under stress, this flaw can become the origin point for a catastrophic failure. A larger beam will often fail at a lower stress level than a smaller beam of the same material. Leonardo da Vinci observed this centuries ago, noting that longer iron wires were proportionally weaker than shorter ones. The volume of potential failure points grows faster than the structure's ability to withstand them. This principle of scale also helps to define which fundamental forces are dominant at different sizes. At the microscopic scale of dust particles or insects, gravity is a weak force. Here, electromagnetic forces like surface tension and static electricity are dominant, allowing an insect to walk on water or dust to cling to a ceiling. As objects scale up, mass, a function of volume, grows exponentially. At the human scale, and certainly at the scale of planets and stars, gravity becomes the dominant force, shaping the structure of the solar system and galaxies. If we move in the opposite direction, toward the molecular scale, the rules of classical physics are replaced by those of the quantum realm. Here, the concept of a solid object begins to change. Particles can exist in a state of superposition, behaving like waves of probability rather than discrete points. This has been demonstrated in the double-slit experiment, where molecules as large as carbon-60 fullerenes have been fired at a barrier with two slits. When unobserved, each molecule appears to pass through both slits simultaneously, creating an interference pattern characteristic of a wave. The buckyball ceases to behave as a single object and instead exhibits wave-like properties. Larger objects do not exhibit this behavior due to a phenomenon called decoherence. A complex object like a human is constantly interacting with its environment, with air molecules, photons of light, and its own internal vibrations. These interactions act as constant measurements, collapsing the quantum wave function and forcing the object into a single, definite state. Scientists are probing the boundary between the quantum and classical worlds. At the LIGO Gravitational Wave Observatory, instruments have measured the motion of 40-kilogram mirrors. Researchers observed that these human-scale objects were being influenced by quantum fluctuations, with movements measured at a scale of 10 to the minus 20 meters. This experiment showed that the effects of the quantum world extend to macroscopic objects, though they are typically masked by thermal energy and the sheer number of particles involved. From the structural integrity of a bridge to the wave-like nature of a molecule, the influence of scale is universal. It is a proxy for a deeper principle. The properties of the universe are not fixed, but are dependent on scale. To cross these boundaries of scale is to enter a new reality, governed by a different set of rules. Conclusion: the journey from a simple cube to the quantum fluctuations of a mirror reveals a fundamental truth. Size is not merely a dimension, but a defining characteristic of physical reality. The square-cube law is more than a biological curiosity or an engineering principle. It is one of the universe's most basic design constraints. It is the invisible architect behind the form of nearly everything. We began with a thought experiment of a 10 times taller human, and saw how they would fail structurally, thermally, and metabolically. This illustrated the core mathematical imbalance. Volume, representing mass and need, increases by the cube, while surface area, representing strength and capacity, increases only by the square. We then saw how this principle is a shaping force in the natural world. It accounts for the pillar-like legs and radiator ears of the elephant, the remarkable strength-to-weight ratio of the ant, and the blue whale's reliance on buoyancy to achieve its immense size. It also explains the hard physical limit on the size of insects. The law's domain extends further. It dictates the integrity of the materials we use to build, making larger structures inherently more susceptible to failure. It draws the boundaries between the fundamental forces, ceding control to electromagnetism at the small scale and to gravity at the large. And at the smallest scales, it gives way to the quantum realm, where our classical intuitions no longer apply. Getting bigger is a structural and physiological challenge because changing size means changing the physical rules that govern an object. An object cannot simply grow without altering its design, materials, and its relationship with the universe. The laws of strength, heat, and energy are all scale-dependent. The square-cube law is, ultimately, a statement of elegance. It is an unyielding and simple piece of mathematics that shapes the function of everything from a cell to a galaxy. It is the silent, ever-present reason why giants remain in the realm of myth, and why our reality is so intricately and precisely constrained. If this journey through the scales of reality has reshaped your thinking, consider subscribing for more explorations into the laws that govern our universe. And now I have a question for you. If you could completely ignore the square-cube law for just one object or creature, what would you scale up or down, and what would be the first thing you'd do with it? Let me know in the comments below. The invisible prison that shapes your reality. We live our lives with a sense of immediate freedom. The choice to stand, to walk across a room, or to reach for a glass of water feels elemental, a direct link between thought and action. We navigate our world with this fundamental assumption, seeing it as a space of open possibility, where our own volition separates desire from reality. But what if this feeling is a perception? A story our mind constructs to make sense of a journey guided by deeper principles. What if the feeling of choosing a path is an interpretation of a journey that was plotted by the laws of physics long before we took the first step? What if every possible path was already written into the fabric of the universe, and space isn't an empty stage, but an invisible architecture that dictates not just where we can go, but who we can be? This isn't a mystical question of fate. It is a question of physics. Today, we'll explore the underlying structure that shapes our reality. We will see how movement might be understood not as pure freedom, but as a strict set of permissions granted by the universe. And how the very structure of space constrains everything that has ever existed to a specific, narrow path. It's a journey that connects our everyday world to some of the deepest principles about the nature of existence itself. The rules of the road. To begin, let's start on familiar ground. The world of classical mechanics, first laid out by Isaac Newton. His laws have described motion with incredible accuracy for centuries, from falling apples to orbiting planets. But we can look at these laws in a new light, not just as laws of motion, but as the first, most fundamental layer of the rules that govern it. Newton's first law, the law of inertia, is a good starting point. It states that an object in motion stays in motion in a straight line, and an object at rest stays at rest, unless acted upon by a force. Rephrased, it means space grants every object a default permission. You're permitted to continue doing exactly what you are doing. In an empty universe, this would be an open road to infinity. But our universe isn't empty. Almost immediately, other forces come into play. A ball rolled across the floor doesn't roll forever, it is slowed by friction. A paper airplane doesn't fly in a straight line. Its path is curved by air resistance and the constant pull of gravity. These forces aren't exceptions to the rule, they are part of the rulebook itself. They are conditions that immediately modify that initial permission to continue. The freedom of an unobstructed road is an idea, but in practice, movement is constantly being shaped by these interactions. Now, let's look at Newton's second law. Force equals mass times acceleration, F equals ma. This is more than an equation, it's a description of the cost of changing a state of motion. To accelerate, to speed up, slow down, or change direction, a force is required. The law states that the amount of force needed is proportional to an object's mass. In this context, mass isn't just stuff, it's a measure of an object's inherent resistance to change. An object with a large mass requires a significant force to alter its path. A tiny electron can be redirected with a small electric field, while a freight train requires a colossal expenditure of energy to start or stop. Permission to accelerate is not granted freely, it has a cost. Finally, there is Newton's third law. For every action, there is an equal and opposite reaction. This might be the most constraining principle of all. It tells us that nothing moves in isolation. To gain permission to move forward, you must have permission to push something else backward. When you walk, it feels as if you are propelling yourself forward. But what is actually happening is that you are pushing the earth backward with your feet. The earth is so massive that it barely moves, but it pushes back on you with an equal force, and that is what moves you. You are granted permission to walk only because you have an entire planet to push against. A rocket in the vacuum of space can't push against anything external. It gets permission to move by throwing its own mass, hot gas, out of its nozzle. The action of pushing the gas backward results in the equal and opposite reaction of the rocket moving forward. In effect, it sacrifices parts of itself to purchase the permission to accelerate. So, even in the classical world of Newton, the picture is one of a tightly regulated system. There is a default permission to remain unchanged, which is immediately altered by forces. Changing motion has a cost proportional to an object's mass, and moving at all requires an interaction. The walls of this structure are already visible. You can only move where, how, and when the forces allow. Your path is not a free choice, but a negotiation with the fundamental principles of the cosmos. But these Newtonian rules are just the beginning. The true architecture lies deeper. The unseen rails. The Newtonian world often operates with the idea of forces acting on objects within a passive, empty space. But what if space itself has a structure that dictates motion before any forces even come into play? This is the next layer of the architecture, kinematic constraints. These are rules built into the geometry of a system that draw the pathways an object is allowed to follow. A good analogy is a train on a track. A train has a powerful engine, but its freedom is limited. It can go forward or backward, and it can stop. It cannot turn left by an inch or swerve. Its path is determined by the iron rails it sits on. The rails themselves aren't a force in the same way as gravity. They are a geometric constraint. They are a feature of the system that says, of all the infinite directions you could move, you are only permitted to move along this one-dimensional line. The train's motion is bound to the path laid out for it. These kinds of invisible rails are all around us, in forms we rarely recognize. In physics, they are called holonomic constraints equations that link the coordinates of a system, reducing its freedom to move. Consider a simple pendulum. A weight on the end of a string can be described by x and y coordinates. But the string has a fixed length. This geometric fact, not a force, but a fact, removes one degree of freedom. The weight cannot be just anywhere, it is confined to move along the arc of a circle. Its path has been pre-drawn by the length of the string. Now, picture a slightly more complex system. An Atwood machine, a simple pulley with a weight on each side of a rope. If one weight is heavier than the other, we know what will happen when they are released. The heavy one will fall, and the light one will rise. Their fates are linked by the rope and pulley, which act as a geometric constraint. The rule is established. For every inch that one weight falls, the other must rise by exactly 1 inch. They cannot move independently. The space, structured by this simple machine, has become a system where the two weights move in a coordinated way, choreographed by the geometry of the system. These constraints also exist on a fundamental level. Imagine running towards a solid brick wall. You don't pass through it. Long before the atoms of your nose make contact with the atoms of the brick, an incredibly powerful barrier appears. This is the electromagnetic force. The electron clouds of the atoms in your body repel the electron clouds of the atoms in the wall. This repulsive field acts as a hard boundary in space. It is a constraint of the highest order, and it says that permission to occupy this region of space is denied. You don't break through the wall, not because you aren't trying hard enough, but because the path through the wall is not a valid trajectory in the universe. It is a forbidden move. The space you thought was open is actually filled with no-go zones defined by force fields. We can't walk through walls or phase through the floor. Our existence is confined to the pockets of space where these repulsive forces grant us permission to be. This idea, that paths are pre-drawn and motion is simply the following of them, is used in a concept from physics and animation called spacetime constraints. Think of an animated character like Pixar's Luxo Jr. lamp. To make it jump realistically, animators don't just calculate forces frame by frame. They often define a start pose and an end pose. Then they apply the constraints. Gravity must be obeyed. Joints can only bend so far, the lamp's base cannot pass through the floor. A computer then solves for the single, most physically plausible path that connects the start and end while satisfying all the rules. What's remarkable is what emerges from this. The lamp appears to anticipate its jump by crouching down. It stretches in midair and squashes on landing to absorb the impact. It looks like it has intention. But this behavior is not programmed step by step. It is an emergent property of solving for the entire path at once, given the constraints. The endpoint influences the beginning. The entire motion is a single, complete trajectory that unfolds once the rules are known. What if our universe works in a similar way? What if our feeling of moving forward through time, making choices as we go, is our limited perspective on a pre-solved, four-dimensional path? This brings us to the deepest layer of this structure, the very fabric of spacetime itself. The blueprint of existence. Newton's laws operate within a static space and time. But Albert Einstein's theory of general relativity revealed that space and time are not a static stage. They are fused into a single, four-dimensional entity called spacetime, and this entity is dynamic, flexible, and the final arbiter of all motion. General relativity reframed our understanding of gravity. In the Newtonian view, gravity is a mysterious force that pulls objects toward each other. Einstein proposed a different idea. There is no pull. Gravity is the consequence of mass and energy warping the geometry of spacetime. The common analogy is a bowling ball placed on a stretched rubber sheet. The heavy ball creates a deep curve in the fabric. If you roll a marble nearby, it doesn't travel in a straight line. It follows the curvature of the sheet, spiraling toward the bowling ball. The marble isn't being pulled by the ball. It's following the straightest possible path, a geodesic asterisk, through a curved landscape. Its path is dictated by the geometry of the surface it's on. Now, scale this up. The sun is the bowling ball. The Earth is the marble. The fabric is four-dimensional spacetime. The sun's mass warps the spacetime around it, and the Earth, in its orbit, is simply following a geodesic, a straight-line path through this curved, four-dimensional space. It is not being pulled, it is coasting. It is following the only path that spacetime permits. The Earth's motion is written into the shape of the universe. This applies to everything. The feeling of being pulled into your chair is not a force. It is the mass of the Earth warping spacetime, and your body is attempting to follow its geodesic downward. The chair provides an electromagnetic force, a hard constraint, that denies you this path. The force you feel is the chair's resistance, preventing you from following the natural curve of spacetime. All motion under gravity, from a falling leaf to a spiraling galaxy, is the effortless following of pathways carved into the cosmos. The universe is not a featureless void. It is a landscape of contours, and everything flows along the paths this landscape defines. Our freedom of movement is a perception, and the paths themselves are the underlying reality. This leads to an even more abstract and powerful concept: configuration space. To describe the state of a single particle in a room, you need 3 coordinates, x, y, z. But for a system of 2 particles, you need 6 numbers to know the position of both x1, y1, z1, and x2, y2, z2. The configuration space for this system is a 6-dimensional mathematical space, where a single point represents one specific arrangement of both particles. For the roughly 10 to the power of 80 particles in the observable universe, you would need a configuration space with about 3 by 10 to the power of 80 dimensions to describe the state of everything at once. This is an impossibly vast mathematical space, a library of all possibilities, containing every conceivable arrangement of matter and energy. But here is the crucial insight: not all of these configurations are accessible. The laws of physics, all of them, from Newton's laws to the curvature of spacetime, act as constraints. They are the rules that carve out impossibly thin pathways through this hyperdimensional space. An electron cannot occupy the same state as another without immense repulsive force. The atoms in your body cannot suddenly rearrange themselves on the moon because that would violate the conservation of energy. The lengths of the bonds between atoms are fixed by holonomic constraints. What remains after this process of elimination is a vanishingly small subset of the original space, a delicate, intricate network of allowed trajectories. Your life, every moment of it, is a single, unbroken line tracing a path through this allowed region. The fact that you exist is evidence that a valid trajectory was found for you. A path that connects your constituent atoms from one arrangement to the next without violating any of the universe's laws. From this perspective, motion is not about choosing a destination. It is about whether a valid path to that destination exists within the constrained landscape of reality. You cannot decide to walk through a wall because there is no permitted trajectory and configuration space that connects you on this side to you on that side. Your existence is predicated on the universe granting your system a valid, continuous path through time. This is the ultimate structure. Its walls are not stone, but mathematics, geometry, and physical law. The ghost and the machine. This physical picture leads us to a deep philosophical question: the problem of free will. The worldview we have built is a form of determinism. It was famously imagined by the 18th-century intellectual Pierre-Simon Laplace through a hypothetical entity. This, Laplace's demon, knows the precise position and momentum of every particle in the universe at one instant. Armed with this knowledge and a perfect understanding of physical laws, the demon could calculate the entire future and retrodict the entire past. For this demon, the universe is a great clockwork mechanism, where every event is a necessary consequence of the state that came before. Einstein's theory of relativity gives this idea a geometric form with the block universe. If all moments in time, past, present, and future, are equally real and coexist within a 4-dimensional spacetime block, then the future is no more open to change than the past. Your life is a finished pattern, a world line, etched into this block. Your subjective experience of passing time is like your consciousness illuminating one slice of this block at a time. In this view, the feeling of choosing your future is an experience of a future that, in a sense, already exists. This is a challenging thought. It suggests that every decision, every feeling, was an unavoidable outcome of prior states. At this point, many people raise an important objection from quantum mechanics. The quantum revolution of the 20th century seemed to challenge the deterministic clockwork of the classical universe. At the subatomic level, reality is not certain, it is probabilistic. A radioactive atom will decay, but it is fundamentally impossible to predict when. Its decay appears to be a truly random event. Does this quantum randomness rescue free will? Does it provide a crack in the structure through which genuine choice can emerge? Many physicists and philosophers would argue, no. Randomness is not the same as agency. An action that is the result of a random quantum event in your brain, a particle swerving left instead of right for no reason, is no more yours than if it had been dictated by deterministic laws. You didn't choose it, it was an outcome of chance. Replacing a deterministic clockwork with a probabilistic one does not automatically create freedom. It is important to note, however, that this is far from a settled question. It remains one of the most active and fascinating areas of debate in both philosophy and neuroscience. Some interpretations of quantum mechanics, like the many worlds interpretation, are fully deterministic. And many neuroscientists believe that in a warm, wet, and chaotic system like the brain, any quantum effects would likely be washed out by the sheer scale of biological processes, leaving the brain to operate in a way that is, for all intents and purposes, classical. So we are left with a complex picture. The universe, as described by its most fundamental laws, appears to be a closed system. Every thought is tied to a brain state. Every brain state is the result of a previous state, governed by the intricate dance of chemistry and electricity. And that dance is governed by the fundamental rules of the cosmos. Your sense of self, your consciousness, may not be the driver of the vehicle. It may be the passenger, observing the scenery of a journey whose path is mapped by physical law. Conclusion: we began with the simple, familiar feeling of deciding to walk across a room. We have ended by looking at a universe that may be a vast, intricate machine, governed by law. We followed the path from Newton's rules, to the geometric rails of constraints, to the ultimate blueprint of spacetime, and found that at every level, a consistent story emerges. Motion is the following of a pre-written script defined by physical law. Existence is the result of finding a valid path through an immense maze of rules. This invisible prison is perhaps better understood as the fundamental architecture of the universe itself. Its walls are the laws of conservation. Its bars are the fundamental forces. Its floor plan is the geometry of spacetime. We are not in this structure, we are a part of it. Our bodies are collections of particles following their geodesics. Our minds are complex patterns emerging from the lawful interactions of those particles. This conclusion can feel like it diminishes the individual. If everything is determined by a law, what is the meaning of our struggles, our choices, our creativity? But perhaps there is another way to see it. Perhaps this structure, this set of constraints, is not a curse, but a blessing. A universe without these rigid laws would not be a universe of freedom. It would be a universe of pure, incomprehensible chaos. It would be a featureless soup of particles, where no order could ever arise. In such a universe, there could be no stars, no planets, no life, and no consciousness. The very constraints that define our path are the same constraints that make an ordered, complex, and beautiful reality possible in the first place. The intricate laws that bind us are the same laws that build us. The geometry that dictates our path is the same geometry that holds the stars in the sky and the atoms in our hands. Maybe freedom isn't about the ability to break the rules, but about the profound privilege of getting to experience a universe that has rules at all. When you next decide to walk across the room, you can feel the ground pushing back up at you. Acknowledge the gravitational landscape you are navigating, and appreciate the long chain of cause and effect that led to the thought to move. You are not a solitary agent breaking new ground. You are a wave, following the contour of the ocean. You are a melody, playing out a score that was written in the Big Bang. And perhaps there is a deeper kind of beauty, a deeper kind of meaning, in playing your part in that cosmic symphony. If this journey into the fabric of reality has been interesting, consider subscribing for more explorations into the nature of the cosmos. And now, we turn the question over to you. Does this vision of a constrained universe feel restrictive, or in a strange way, elegant? Let us know in the comments below. The universal law that erases almost everything. What if the universe we see is just a ghost? A faint echo of what could have been? We look up at the night sky, a glittering blanket of stars and galaxies, and we feel this sense of infinite possibility. It looks like a canvas where any story could be painted, any reality could unfold. We see a universe that seems full of choices and endless branching paths. But what if that feeling, that deeply human intuition of boundless potential, is the most profound illusion of all? What if the universe operates on a strict, silent, and unbreakable rule? A rule that doesn't create, but erases. A law that filters out almost every reality you can imagine before it can even exist, leaving behind only the most stable, most resilient patterns. This isn't just a philosophical thought experiment. It's a startling consequence woven directly into the fabric of space and time. This is the story of the cosmic sieve. It's the story of the universal law that erases almost everything, and how we, against all odds, are part of the pattern it couldn't break. Imagine a sculptor with a block of marble the size of infinity. The sculptor doesn't add anything to it. They only take away, chipping away every single piece that isn't the final statue. The universe is that sculptor. The laws of physics are its chisel. And reality, the world we experience, is the statue that's left after an almost infinite amount of marble has been carved away and tossed aside. Every potential universe, every star that could have been, every form of life that might have existed, they're all just chips of marble on the workshop floor. We are living inside the finished sculpture, completely unaware of the near total extinction of possibilities that our existence required. We mistake the masterpiece for the whole block. So today, let's pull back the curtain on this cosmic editing process. We'll explore the fundamental laws that act as the ultimate judge, deciding what gets to be real. We'll see how these rules erase potential stars, snuff out fledgling life, and may have already sealed the fate of countless alien civilizations. This is the story of the Great Erasure, and it begins with the very code of creation itself. The first and most profound filter that any reality has to pass through is the most fundamental of all, the settings of the universe itself. We call them the fundamental constants of nature, numbers that define the strength of gravity, the speed of light, the charge of an electron. They seem like random values, but they hold the power of life and death over entire cosmos. Think of it like the source code for a huge computer simulation. If you change just one critical number in that code, even by a tiny bit, the whole program crashes. Our universe is that program. And it seems to have been written with a terrifying precision. Let's start with gravity. It feels familiar, a gentle force tethering us to the Earth. But the number that sets its strength is balanced on a razor's edge. If it were just a tiny bit stronger, the stuff from the Big Bang wouldn't have had enough oomph to escape its own pull. The brand new universe would have expanded for a moment and then immediately collapsed back on itself in a big crunch. An entire cosmos, erased in an instant. No galaxies, no stars, no planets. A failed universe, deleted. Now, what if gravity were just a fraction weaker? The Big Bang's expansion would have been too powerful. Matter would have flown apart so fast that it never would have had the chance to clump together. The universe would have become a thin, cold, and eternally expanding soup of lonely particles. No clusters of gas to form the first galaxies. No galaxies to host the first stars. Another reality, erased. A universe of lonely atoms, drifting forever in an endless void. The same terrifying precision applies to the forces holding atoms together. The strong nuclear force is what binds protons and neutrons in an atom's core. If this force were just a few percent weaker, it couldn't overcome the repulsion between protons. Simple elements like deuterium wouldn't be stable. Stars would never be able to fuse hydrogen, their main fuel. The celestial engines that forge the elements for life would never even turn on. The universe would be a dark, sterile place filled with nothing but hydrogen. And if the strong force were a few percent stronger? The consequences would be just as bad. Hydrogen would fuse so easily, so violently, that stars would burn through all their fuel almost instantly. The Big Bang itself would have fused all the hydrogen into heavier elements, leaving nothing behind to power stars like our Sun. Either way, the result is the same: erasure. A universe without the long-lived furnaces it needs to build anything interesting. This fine-tuning principle applies to almost everything in physics. The mass of a neutron, the strength of electromagnetism, if you nudge any of these values, the consequences cascade into a universe that can't form the basic building blocks of complexity. Stable atoms might not exist. The periodic table would be a wasteland. Chemistry itself, the very dance of molecules that makes life possible, would be forbidden. This is the first great filter. Before a single star can shine, before one planet can form, the universe has to pass an unbelievably difficult test. Its own laws have to be perfectly balanced. We don't know why our universe has these specific settings. Was it a cosmic lottery, and we just happened to be in the one universe out of a near infinity that won? Or is there some deeper reason we don't understand? Whatever the answer, the implication is staggering. Countless possible universes. Realities with slightly different rules aren't just empty. They're impossible. They were erased by their own source code, filtered out by the cosmic sieve before they could even begin. The reality we're in isn't one option among many. It's a survivor. So, even if a universe gets the settings just right, allowing stars to shine and atoms to bond, it immediately runs into a second, relentless filter. This one is more subtle than gravity, but it's even more inescapable. It's the silent, organizing principle of the cosmos and the source of the arrow of time. It's the second law of thermodynamics, but you probably know it as entropy. The second law is simple. In an isolated system, disorder, or entropy, always increases. Things fall apart. Order gives way to chaos. A hot cup of coffee always cools down as its ordered heat scatters into the air. It never spontaneously gets hot again. A sandcastle on the beach is always worn down by the wind and waves into a random pile of sand. It never spontaneously builds itself back up. This one-way street from order to disorder is why time seems to flow forward. This law isn't a suggestion, it's a statistical certainty. And it acts as a ruthless filter for any structure that dares to appear. Every complex thing, a star, a planet, a tree, a human body, is a pocket of exquisite order. A star isn't a random gas cloud. It's a highly ordered sphere balancing the crush of gravity with the outward pressure of fusion. A living cell isn't a random soup of chemicals. It's a microscopic city of mind-boggling complexity, with molecular machines performing precise tasks. Each of these structures is a wild, improbable island of order in a universe that prefers chaos. The second law says that the tide of disorder is always coming in. To exist, a complex structure has to fight a constant, desperate battle against being erased by entropy. So how does it fight? It has to cheat. A complex system can only maintain its internal order by importing energy from outside and exporting disorder back into its environment. It has to make its surroundings more chaotic to preserve its own little bubble of order. A star does this beautifully. It consumes its highly ordered fuel, hydrogen, and through fusion, creates light and heat. In the process, it spews vast amounts of disordered radiation into the cosmos, increasing the overall entropy of the universe. It survives by making its surroundings messier. Life is the ultimate entropy cheater. A plant takes in the ordered energy of sunlight and simple molecules to build its complex structure, releasing disordered heat in the process. You're doing it right now. You maintain the incredible order of your body by eating ordered chemical energy, food, and releasing disordered waste heat into the environment. Every breath you take, every meal you eat, is a bargain with the second law. You're borrowing order, and you're paying the universe back with chaos. This is the tyranny of the arrow of time. It says nothing is permanent. Any system that can't find a reliable source of energy, or can't efficiently pump out its excess entropy, is immediately and mercilessly erased. A star that runs out of fuel collapses, its elegant structure obliterated. An organism that can't find food starves, its body decomposing as it loses the energy needed to fight off decay, its order dissolving back into randomness. This law erases a whole new set of hypothetical realities. It erases any perpetual motion machine. It erases any form of life that could exist without an energy source. It erases any civilization that could grow without consuming resources and producing waste. Entropy is the great equalizer. It's the deadline imposed on every star, every planet, and every living thing. It's the universal law that guarantees nothing lasts forever. Our existence is just a temporary rebellion against the inevitable. We are a fleeting pattern that has, for a little while, figured out how to ride the wave of cosmic chaos. But that wave is always there, waiting to reclaim the order we've borrowed. We've seen how the laws of physics act as a filter, erasing entire universes and dismantling any structure that can't fight the tide of entropy. So, how does this apply to that big, unsettling question? Are we alone? This brings us to the Fermi paradox. The math is simple and haunting. Our galaxy has up to 400 billion stars. A huge number of those likely have planets. Many of those should be in the habitable zone, where liquid water can exist. If even a tiny fraction of those planets develop life, and a tiny fraction of that life becomes intelligent, our galaxy should be buzzing with civilizations. Given the age of the universe, many should be millions of years older than us, with more than enough time to colonize the galaxy. Their presence should be obvious. And yet, we hear nothing. The cosmos is silent. This huge gap between what we expect and what we see is the paradox. Where is everybody? In the 1990s, economist Robin Hanson proposed a chilling answer called the Great Filter. The idea is simple. Somewhere on the path from non-living matter to a galaxy-spanning supercivilization, there must be a step, or steps, that is so incredibly hard to get through that almost no one ever makes it. This filter is the cosmic sieve applied directly to life. It explains the silence. We don't hear from alien empires because they are statistical impossibilities. They are the realities that got erased. To understand the filter's power, let's break down the journey into a few key steps. At least one of them must be the barrier. 1. The right star system. **** a stable planet, in a habitable zone, around a long-lived star. This is probably pretty common. 2. Abiogenesis. ***, life has to arise from non-living chemicals. This is where it gets tough. On Earth, it took almost 1 billion years for the first simple cells to appear, and we've never been able to replicate it in a lab. This could easily be a monumental filter. The universe might be full of beautiful, sterile planets where the spark of life just never happened. 3. Simple prokaryotic life. ***, the emergence of single-celled organisms like bacteria. 4. Complex eukaryotic life. ***, the leap from simple cells to complex cells with a nucleus and specialized parts. This was another huge jump. On Earth, There was a gap of nearly 2 billion years between simple cells and complex cells. 2 billion years of apparent stagnation. This is another top candidate for the Great Filter. 5. Multicellularity. Individual cells teaming up to form complex organisms. This has happened independently over 40 times on Earth, so this step might not be that hard. 6. Tool using intelligence. A species evolving brains capable of abstract thought and manipulating its environment. Looking at millions of species on Earth, this seems exceptionally rare. 7. Advanced technological civilization. This is where we are right now. Harnessing energy on a global scale and starting to explore space. 8. Galaxy-wide colonization. The final step, where a civilization spreads across the stars and becomes effectively immortal. The terrifying question is, where on this list is the Great Filter? The answer dictates our entire future. There are two broad possibilities. First, the optimistic one. The Great Filter is behind us. Maybe the origin of life, or the jump to complex cells, was the 1 in a trillion event. If that's true, we're the first, or among the first, to make it through. We won the cosmic lottery. The silence we hear is an empty galaxy waiting for us. This is why some say that finding even fossilized bacteria on Mars would be the most terrifying news in human history. Why? Because it would mean that starting life isn't the filter. It would imply the filter is still waiting for us. This leads to the pessimistic scenario. The Great Filter is ahead of us. In this view, the universe might be teeming with simple life. But something stops them from ever reaching step 8. Something erases them. What could this future filter be? It could be self-destruction. The very technology that gives a civilization its power, nuclear energy, artificial intelligence, genetic engineering, might inevitably lead to its downfall. Perhaps any species smart enough to split the atom will always, eventually, use it to destroy itself. Or perhaps a civilization will always burn through its planet's resources and trigger a climate collapse it can't survive. In this case, the filter is a final, brutal test of wisdom. Or, the filter could be external. A nearby supernova could sterilize a planet. A random asteroid could cause an extinction-level event. The universe doesn't care about your progress or philosophy. It just rolls the dice. The Great Filter is the ultimate expression of the law of erasure. It suggests the silence of the cosmos isn't an empty stage waiting for a play, but a graveyard, filled with the ghosts of actors who never made it past the first act. We've journeyed through a universe of erasure. We've seen how the wrong physical constants can delete a cosmos, how entropy dismantles order, and how the Great Filter might prune the tree of life. It's a bleak picture. But what if we've been looking at it all wrong? It's time for the big reveal. The universal law isn't about destruction. It's about selection. The universe isn't a malevolent editor, gleefully deleting failed drafts. It's an impartial testing ground. It throws every possibility against the wall of reality and just sees what sticks. What we call reality is simply the collection of patterns that were so stable, so resilient, that the laws of the universe couldn't break them. Think about a single atom of hydrogen, a proton and an electron, bound together. This isn't a random arrangement. It's an unbreakable pattern. The laws of quantum mechanics say this is a stable, low-energy configuration. You could have a universe filled with trillions of loose protons and electrons, but they would inevitably find each other and settle into this stable pattern. The hydrogen atom pattern persists because it's a solution to the equations of physics. It works. A star is a much more complex, but still temporarily stable, pattern. It's a breathtakingly elegant balance between two cosmic forces, the inward crush of gravity and the outward blast of fusion. For billions of years, this pattern holds. The stars we see are the ones that found that unbreakable balance point. This idea scales all the way up. Our solar system is a stable pattern of orbital mechanics. The DNA molecule is a pattern that mastered information storage and self-replication, allowing it to persist for billions of years. Even a mathematical truth, like 2 plus 2 equals 4, is a purely abstract pattern so unbreakable it would be true in any universe you can imagine. This changes everything. The question is no longer, why did our universe happen? The real question is, out of all possible patterns, why are these the ones that were unbreakable? What we see as the creation of the universe was maybe the discovery of these stable patterns. Reality isn't an act of infinite invention, but an act of near-infinite filtration. Your existence, the fact that you are here, thinking these thoughts, is a testament to this principle. You aren't a random fluke. You are a continuation of a chain of unbreakable patterns. The atoms in your body are stable quantum configurations. The cells they form are stable biological systems that mastered the art of fighting entropy. Your consciousness is an emergent pattern, running on a biological computer that is itself the result of 4 billion years of filtration, what we call evolution. We aren't just living in the universe. We are the patterns the universe couldn't erase. We are the sculpture left after the marble of impossibility has been chipped away. The reality we inhabit isn't the default state, it's the extraordinary exception. It's the ghost of a near infinity of failed worlds, the one configuration stable enough to look back and wonder why. We started our journey by imagining a cosmos of infinite possibility. Now, we see it through a different lens. The universe is haunted. It's haunted by the ghosts of all the realities its own laws erased. Every empty corner of space whispers of the universes that collapsed in on themselves. Every cold, dark star is a monument to the inescapable power of entropy. And the profound, deafening silence between the stars may just be the sound of the great filter at work, the sound of a million potential civilizations that were erased before they could ever call out. But this perspective shouldn't inspire despair. It should inspire a deep and profound sense of awe. It reframes our place in the cosmos. We aren't just a mediocre product of random chance in a universe overflowing with life. We might be something far more precious. We are the survivors. Our existence is an almost impossible chain of victories against the law of erasure. For our universe's constants to be just right for life is a triumph. For life to have sparked from non-living matter is a triumph. For that life to have navigated the treacherous journey to complexity and consciousness is a triumph. And now, we stand at our own precipice. Our technological civilization is a new pattern, a new experiment being tested by those ancient laws. The challenges of our time, climate change, nuclear proliferation, unchecked technology, they aren't just political problems. They're tests of our pattern stability. Can we, as a species, become an unbreakable pattern? Can we learn to manage our energy and resources, to cooperate on a global scale, to use our immense power with wisdom? Or are we just another beautiful, complex, but ultimately unstable pattern, destined to flicker for a brief cosmic moment before being erased, leaving only silence behind? The universe doesn't care about our hopes or fears. It doesn't play favorites. It only tests patterns. It tests them for resilience, for stability, for endurance. The law of erasure is absolute. We are not a product of infinite chance, but the survivors of a near-total extinction of possibilities. We are the pattern that the universe could not erase. At least, not yet. The universe is filled with questions that challenge our very understanding of what it means to be. If you believe these questions are worth asking, subscribe for more explorations into the cosmos. And now we turn the question to you. If the great filter is real, where do you think it is? Behind us, in our past? Or ahead of us, in our future? Let us know your thoughts in the comments below. It has long been an intuitive concept that any distance can be divided in half, that one can zoom in forever. This idea feels foundational to a smooth, continuous reality. However, at the most fundamental scales, this may not be the case. There appears to be a point where the universe itself presents a limit. This is not a discussion about the limits of technology, of building a better microscope or a more powerful particle accelerator. It concerns a fundamental barrier that seems to be part of the fabric of spacetime. A point where, if we channel more and more energy into smaller regions of space, a curious consequence emerges. The universe, it seems, has a built-in limiting mechanism. In this exploration, we will trace a path to a place where the laws of physics, as we understand them, conspire to prevent us from seeing further. A place where space itself behaves in a way that stops us from looking closer. We will examine the evidence for the smallest we can go, right before our description of space no longer applies. Consider the process of observing progressively smaller scales. We move past mountains and microbes, past atoms and their electrons, into a domain governed by energy and probability. As we attempt to probe deeper, a principle seems to emerge. The laws of physics themselves may prevent observation beyond a certain point. Today, we will explore this boundary, a frontier where our current understanding of reality reaches its limit. Our inquiry begins not in deep space, but with a familiar object. Consider a single grain of sand. To us, it is small. Yet, on the scale of our investigation, this grain of sand is a vast landscape we must traverse to reach the truly small. If we were to scale ourselves down, this grain would appear as a desert of crystalline structures. Our first tool for this inward observation is light. For centuries, optical microscopes have used photons to reveal the unseen world of bacteria or the structures of a fly's eye. But light has its limits. Each photon has a wavelength, which acts as a ruler defining the smallest object it can resolve. To see something smaller than the wavelength of visible light, a different tool is needed. It would be like trying to determine the shape of a single grain of sand while wearing thick gloves. The instrument is too blunt for the task. This leads us to a sharper tool, the electron microscope. In quantum mechanics, particles like electrons also have a wave-like nature. By accelerating them to high speeds, their effective wavelength can be made thousands of times shorter than that of visible light. With this, a new level of reality becomes visible. We can observe viruses, individual proteins, and the molecules that form the basis of life. We are descending through the layers of existence. A human hair appears as a massive, textured cylinder. We move past its surface, into the keratin proteins that form its structure, which are themselves composed of long chains of molecules. These molecules, in turn, are built from something more fundamental, atoms. Here, at the atomic scale, our classical intuition begins to fail. We are entering a realm governed not by familiar mechanics, but by the probabilistic laws of quantum theory. The solid ground of our everyday experience is about to be replaced by a shimmering field of possibilities. This is our first major stop on the path to the ultimate limit. In cosmic terms, we are still a great distance from our final destination. We arrive at the atom, a carbon atom, perhaps, from our grain of sand. The common image of an atom is a miniature solar system, with electrons orbiting a dense nucleus. This depiction is misleading. As we reduce our scale, the first thing we would notice is emptiness. The atom is a domain of profound emptiness. If an atom were scaled to the size of a cathedral, the nucleus would be no larger than a grain of sand at its center. The electrons would not be tiny planets in fixed orbits. Instead, they would exist as a cloud of probability, a diffuse haze filling the entire volume, representing the regions where an electron might be found. It is not in one location, it exists as a superposition of all its possible locations at once. This is the first notable observation on our journey. Solid matter is mostly an illusion. The sensation of touching a table is not the result of hard spheres making contact. It is the electromagnetic force generated by these electron clouds repelling each other. In a sense, you have never truly touched anything. Your electron clouds have merely approached those of another object closely enough to feel a repulsive force. This emptiness is almost absolute. An atom is often described as being over 99.9999% empty space. Yet even this is a simplification. The empty space is a field of quantum activity. It is filled with virtual particles, pairs of matter and antimatter that emerge from the vacuum for brief moments before annihilating, borrowing energy from the void before returning it. This quantum foam is the medium in which all other particles exist. Now, we navigate this emptiness toward the center, toward the nucleus. As we approach, we find that while it occupies a minuscule fraction of the atom's volume, it contains over 99.9% of its mass. This is where the substance of matter resides, packed into a dense volume. Here, we find protons and neutrons, bound by a force of immense strength. Our journey must now go deeper, into a world held together by the strongest force in nature. Inside the nucleus, we have moved from the probabilistic world of electron clouds to a domain of brute force. Protons and neutrons are held so tightly that the electromagnetic repulsion between the positively charged protons should tear the nucleus apart. That it does not is evidence of a stronger power, the strong nuclear force. The strong force is the most powerful of the fundamental forces, over 100 times stronger than electromagnetism, but it only operates over incredibly short distances. If two bound particles are pulled apart slightly, the force between them increases, similar to stretching a durable elastic band. This property, known as color confinement, is what maintains the nucleus's stability. If you pull them too far, the energy invested becomes so great that it converts into mass, via E equals mc squared, and a new pair of particles forms between them. You cannot isolate its constituents. For a long time, protons and neutrons were considered fundamental. However, as more powerful particle accelerators were developed, we found they were composed of something smaller, quarks. Each proton and neutron is made of a trio of these elementary particles. They have different properties, or flavors, and are the building blocks of most visible matter. Our focus must now go deeper, to a single quark inside a proton. Here, we encounter a paradox. According to the standard model of particle physics, a quark has no discernible size. An electron is also considered a point particle. This means that, as far as our theories and experiments can determine, it occupies zero spatial volume. It has properties like mass and charge, but no width or height. Our measurements have probed the electron down to a scale of approximately 10 to the power of -22 meters, and it still behaves as a dimensionless point. This presents a problem for our inquiry. If a particle has no size, what does it mean to zoom in on it? It seems to undermine the concept of our journey. If reality is made of these dimensionless points, it would suggest that space can be divided forever. This is where the universe begins to push back. Our journey inward is about to intersect with two fundamental principles of reality. The first governs the act of observation itself and places a limit on what we can ever know. We are approaching the first barrier, the Heisenberg uncertainty principle. The idea of a dimensionless particle suggests a perfectly smooth and continuous space. However, the universe has other properties. To continue our journey and see a quark or an electron, we need a probe. We need to interact with it. As discussed, to see smaller objects, one needs a probe with a shorter wavelength. To see an atom, we required the short wavelength of an electron. To see inside a proton, we need a shorter wavelength still. This means we must use a particle, for instance, a photon, that has an incredibly short wavelength. In quantum mechanics, a shorter wavelength corresponds to higher energy. To resolve smaller distances, one must use higher energies. To see the infinitely small, it would seem to require an infinite amount of energy. This brings us to Werner Heisenberg and his uncertainty principle. It states that one cannot simultaneously know the exact position and momentum of a particle. The more precisely you measure its position, the less precisely you can know its momentum. This is not a limitation of our measuring instruments, it is a fundamental property of reality. There is an inherent fuzziness to the universe at its smallest scales. As we attempt to look deeper into the structure of a point particle, we must bombard it with photons of progressively higher energy. We increase the power of our conceptual microscope, shortening the wavelength to resolve smaller and smaller distances. The energy required becomes immense. We are concentrating a great deal of energy into a very small region of space. For a time, this method is effective. Our particle accelerators function on this principle, concentrating energy to probe tiny scales. But as we continue to increase the energy, another factor becomes significant. A force that has been irrelevant for our entire journey, a force so weak on the scale of atoms that it was negligible, begins to emerge. This is the force of gravity. Its appearance will form the second and final wall. On our journey from a grain of sand to the subatomic realm, gravity has been functionally absent. At the atomic scale, the electromagnetic force between two protons is roughly 10 to the power of 36 times stronger than the gravitational force between them. For most purposes in particle physics, gravity can be ignored. However, gravity has a unique relationship with energy. And in our effort to see smaller scales, we have been gathering a very large amount of energy. Here, we turn to Albert Einstein. His equation, E equals mc squared, shows that energy and mass are interchangeable. Energy has a mass equivalent, and mass is a form of concentrated energy. As we use our hypothetical microscope to probe ever smaller distances, we must use photons of ever-increasing energy. We are packing more energy into a tiny volume of space. According to Einstein, by concentrating energy, we are also, in effect, concentrating mass. The point we are observing becomes incredibly energy-dense, and therefore, mass-dense. And mass creates gravity. Einstein's theory of general relativity described gravity not as a traditional force, but as a curvature of spacetime. Massive objects warp spacetime, and other objects follow these curves. A planet orbiting a star is moving in a straight line through spacetime that has been warped by the star's mass. At the scale of an atom, the particle masses are so small that their effect on spacetime is practically flat. But we are no longer dealing with the tiny rest mass of an electron. We are dealing with the colossal equivalent mass of the energy we are using to probe it. As we continue to increase the energy of our probe to achieve a shorter wavelength, the energy density increases dramatically. The equivalent mass in that small region becomes very large. The gentle, negligible dimple in spacetime becomes a steep, curving funnel. Gravity becomes the dominant force in this microscopic environment. We have arrived at a convergence. The law of the very small, the uncertainty principle, has required us to gather immense energy. The law of the very large, general relativity, dictates that this energy will warp spacetime. The two pillars of modern physics, quantum mechanics and general relativity, are finally meeting. Their collision, at this tiny point, is about to create the ultimate barrier. We are at the precipice. From quantum mechanics, we know that to observe a region of size, d, we need a particle with a wavelength no larger than d. This implies a minimum energy, dictated by the uncertainty principle. The smaller the d, the more energy is required. From general relativity, we know that if we concentrate a mass, m, into a sphere smaller than its Schwarzschild radius, it will collapse to form a black hole. An event horizon will form, a boundary from which nothing, not even light, can escape. For most of physics, these two rules operate in separate domains. The energy needed to probe an atom is not enough to create a significant gravitational field. The Schwarzschild radius of a single electron, based on its rest mass, is an exceptionally small number, far smaller than any scale we are discussing. However, we are not dealing with the electron's rest mass. We are dealing with the mass equivalent of the energy used to probe it. And here, we reach the conclusion of our thought experiment. As we try to look at smaller scales, the required energy increases. The equivalent mass increases. Therefore, the Schwarzschild radius for that concentration of energy also increases. At the same time, the size of the region we are trying to observe is decreasing. At one specific, small scale, these two values meet. This scale is known as the Planck length, approximately 1.616 times 10 to the minus 35 meters. At this scale, a theoretical limit is reached. If you try to observe a region smaller than the Planck length, the energy required would be so immense that its equivalent mass, packed into that volume, would have a Schwarzschild radius larger than the region you are trying to observe. The act of observation itself would trigger a collapse. The location you are trying to observe would become a microscopic black hole. An event horizon would form, enclosing the region you were attempting to probe. The information you sought would be trapped inside, inaccessible to the outside universe. Any attempt to see what is happening at that scale is blinded by the creation of this information barrier. Using even more energy to get a better look would only compound the problem. More energy means more equivalent mass, which creates a larger black hole, hiding a larger region of space. Physics itself appears to conspire to prevent observation at smaller scales. This does not necessarily mean that space is pixelated, or that the Planck length is a literal minimum distance. Our current theories are incomplete. What this thought experiment demonstrates is the scale at which quantum mechanics and general relativity collide and produce a paradox. It is the scale at which our current understanding of physics breaks down, and where spacetime as a smooth, continuous fabric ceases to be a useful description. The black hole barrier is a prediction that emerges when you push our two best theories of reality to their absolute limits. This exploration to the smallest scales reveals something about the structure of our universe. It is a system with rules so fundamental, they create their own boundaries. The Planck length is not a physical wall, but a horizon, a limit on what we can know, dictated by the nature of reality itself. What do you think happens in the realm beyond the Planck length? Is it a sea of quantum foam, vibrating strings, or something for which we do not yet have concepts? Feel free to share your thoughts in the comments. If this kind of calm exploration helps you think, please consider liking the video and subscribing for more inquiries into the questions of the universe. Your support allows us to continue these investigations. We have traveled from the familiar scale of a grain of sand, through the emptiness of the atom, past the constituents of the nucleus, and arrived at a barrier made not of matter, but of the laws of physics. We found that the attempt to see smaller and smaller scales is, eventually, self-defeating. The act of looking, when taken to its extreme, obstructs the view. The Planck length emerges not as a fundamental pixel of space, but as the threshold where gravity and quantum mechanics must be reconciled into a single, deeper theory of quantum gravity. It represents the limit of our current questions, where concepts like space and distance may lose their meaning. The universe does not forbid smaller distances with a physical sign. Instead, it uses its own rules, the uncertainty of the quantum world and the spacetime curvature of relativity, to draw a veil. It suggests that while you can ask the question, you can journey to the boundary, but you may never see what lies beyond. Space itself prevents us from breaking it, by collapsing a point of inquiry into a microscopic prison of gravity. And in that elegant limitation, we find one of the deeper truths about our cosmos. Consider your hand, and the table it rests upon, the floor beneath your feet, the walls that enclose the room. They feel solid, immovable. We place our trust in them. We have an unshakable faith that the floor will support our weight, that a wall will resist our push. This experience of solidity, of a definite presence, is perhaps the most fundamental perception of our reality. It is an assumption so deep it is rarely recognized as one. And yet, this feeling of solidity is an interpretation of a much stranger truth. The atoms that compose your hand and the atoms that form the table are, in fact, almost entirely empty space. A void so vast that the solid matter within is functionally insignificant. It is a fact that borders on the absurd. If you and the world around you are mostly empty, a profound question arises. Why is reality not a ghost? Why do you not pass through the floor and fall toward the center of the earth? Why does your hand not phase through the table like a phantom? The answer lies not in the tangible world of our senses, but deep within the quiet and profoundly strange realm of the quantum. There, an invisible architecture, a set of unbreakable rules, governs the behavior of matter, deciding what can be and what cannot. This is not a gentle suggestion. It is a force of absolute repulsion, a fundamental no that tells matter where it can and cannot go. It is the reason our reality does not dissolve into a thin, probabilistic soup. Today, we will look past the illusion of the solid world and into the unseen furnace where it is forged. Imagine, for a moment, your hand passing through a solid oak table. Not breaking it, but phasing through it, your atoms moving between its atoms. This is, of course, impossible in our experience. But to ask why it is impossible reveals the limits of common sense. To say, because it's solid, is merely to restate the observation. The true reason has little to do with our intuition. It is because the universe itself forbids it. The very fabric of existence enforces a set of rules so strict they create the unyielding barrier we perceive as solid. To understand those rules is to see that the stability we take for granted is one of the most elegant and powerful processes in the cosmos. To understand why things are solid, we must first ask what they truly are at their most fundamental level. Here, we find the familiar models begin to fade. The image of the atom we learned in school, tiny electron, planets, orbiting a nuclear sun, is a simplification. It provides a sense of order, of predictable paths. But the reality is far more ephemeral. An electron is not a tiny, solid point. A more accurate picture is that an electron is an excitation within a vast, invisible field that permeates all of space, the electron field. Think of space not as an empty stage, but as a silent, invisible ocean. An electron is a ripple in that ocean, a localized vibration. The universe, at its core, is not made of things, it is made of these fields. The chair, the air, the light itself, all are just patterns and ripples moving through this fundamental medium. Here we encounter the first layer of strangeness. This ripple, this particle, does not have a single, definite location. It exists in a superposition, a haze of all its possible locations at once, a wave of probability. It is not that we simply do not know where the electron is. It is that the electron itself has not settled on a single position. It is smeared out in a cloud of potential. This is the famous uncertainty principle, which holds that one cannot simultaneously know a particle's exact position and its exact momentum. The more precisely one is known, the less certain the other becomes. At this foundational level, reality is not solid and definite. It is a shimmering, probabilistic dance. Quantum physics describes a world of pure potential, where particles exist in multiple states at once and only resolve into a single state upon interaction. We see this in the double-slit experiment. When single electrons are fired at a barrier with two slits, they do not behave like particles. If their path is not observed, they act as if they pass through both slits simultaneously. They interfere with themselves, like a wave, creating a pattern on the screen behind that would be impossible for a single solid object. It is only when a detector is placed to watch which slit the electron goes through that it abandons this wave-like behavior, chooses a single path, and the interference pattern vanishes. This is the foundation of our universe. Every atom in your body, every star in the sky, all of it is built from these wisps of probability. This deepens the puzzle. If the building blocks of reality are so ghostly and indeterminate, how do they come together to build a world that feels so concrete and reliable? If everything is just a wave of possibilities, why does the floor not simply become a possibility somewhere else? The stability we experience seems to be a direct contradiction to the quantum chaos that underpins it. It is like building a cathedral out of smoke. The answer begins not with the particles themselves, but with the rules that govern their interactions. Our journey from the quantum realm to the solid world is guided by two main principles. They are the enforcers that take the chaos of probability and shape it into the form of reality. The first is a familiar force, electromagnetism. The second is a principle you may not have heard of, but it is arguably one of the most important rules for the existence of structure, the Pauli exclusion principle. First, electromagnetism. As you bring your hand toward a table, the atoms in your hand, mostly empty space, filled with clouds of electron probability, draw near the atoms of the table. The outermost part of every atom is this electron cloud, which carries a negative electric charge. And as we know from simple magnets, like charges repel. As the electron clouds of your hand's atoms approach those of the table's atoms, a powerful repulsive force emerges. It is the electromagnetic force. It acts as a powerful shield. The electrons in your hand are violently repelling the electrons in the table, and it is this invisible cushion of repulsion that you perceive as the sensation of touch. In a very real sense, you have never truly touched anything. What you feel as contact is the electromagnetic fields of atoms pushing against each other. But this is not the whole story. If it were, reality might still feel mushy. Electromagnetism explains why objects resist passing through one another, but it does not fully explain their stable and definite volume. Why don't all the electrons in an atom, under the immense pull of the positive nucleus, simply collapse inward? Why don't the atoms in a stone, when squeezed, simply merge into a denser blob? This is where our second principle enters, the Pauli exclusion principle, proposed by the physicist Wolfgang Pauli in 1925. It is a simple rule with profound consequences, an ultimate organizer of the quantum world. It states that no two identical fermions can occupy the same quantum state at the same time. Let us break that down. Fermions are the particles that make up matter: electrons, protons, and neutrons. They are the matter particles. The other class, bosons, are force-carrying particles, like photons. Bosons are social. They can clump together in the same state, which is how a laser works. Fermions, however, are individualists. The exclusion principle is their fundamental law. A quantum state is a particle's unique address, defined by numbers that describe its properties, like its energy level and its spin. The principle dictates that within an atom, every single electron must have its own unique address. They cannot be perfect twins. Imagine an atom as a large apartment building. Each floor is an energy level, or shell. Each apartment is an orbital, a region of probability where an electron might be found. The Pauli exclusion principle acts as a strict housing code. An orbital can hold, at most, 2 electrons, and only if they have opposite spins. 1 spin up, 1 spin down. This difference is enough to give them distinct states. But a third electron cannot be forced into that same orbital. The universe forbids it. This is the true origin of structure. Electrons cannot all collapse into the lowest energy level. Once that level is full, the next electron is forced by the exclusion principle to occupy a higher, more energetic orbital. This forced stacking creates the shells of electrons, giving the atom its volume. Now, let's return to your hand and the table. When you press down, you're trying to force the electron clouds of your atoms to overlap with the electron clouds of the table's atoms. You are attempting to make trillions of electrons from your hand occupy the quantum states already filled by the electrons in the table. And the universe, through the Pauli exclusion principle, says no. This is not a suggestion. It is an absolute law. The resistance you feel is called degeneracy pressure. It is a quantum repulsion that has nothing to do with charge. It would exist even if electrons were neutral. It is a fundamental resistance of matter to being compressed into the same space. This is the invisible force field. It is a partnership of two effects: the electromagnetic repulsion pushing clouds apart, and the Pauli exclusion principle providing the ultimate structural integrity, declaring, this space is taken. Together, they create the illusion of a solid surface from a void of probabilistic fields. It is not that atoms are solid balls. It is that the rules governing them are unyieldingly rigid. This principle underpins the entire structure of the periodic table and all of chemistry. Without it, all atoms would be indistinct, and complex structures, like life, could never exist. The force is so powerful it supports not just tables, but stars. In a white dwarf, gravity has crushed atoms, stripping electrons from their nuclei. The only thing preventing the star's total collapse is the degeneracy pressure of these electrons, all refusing to share the same quantum state. In even more massive stars that collapse further into neutron stars, it is the neutrons, also fermions, that hold the star up against gravity, creating a substance so dense a sugar cube-sized amount would weigh as much as all of humanity. The next time you lean against a wall, consider what is truly happening. You are being supported by the same fundamental principle of quantum aloofness that prevents dead stars from vanishing. Solidity is not an intrinsic property of matter. It is the consequence of an unyielding law, imposing order on the underlying chaos. We have established the foundation of solidity. The standoff between electromagnetism and the Pauli exclusion principle gives matter its structure. But this is only part of the story. A world that is solid but unpredictable would be just as chaotic as a ghostly one. Why does the world not only exist, but also behave in an orderly fashion? Why do falling objects follow a predictable path? Why is the universe reliable? The answer lies in a deeper layer of physical law: the conservation laws. Conservation of energy, of momentum. These are not just useful ideas, they are unwavering rules. Energy cannot be created or destroyed, only transformed. The total momentum of a system remains constant. These laws provide the framework for cause and effect, ensuring the universe operates according to a consistent logic. But where do these powerful laws come from? The answer is one of the most beautiful ideas in physics, discovered by the mathematician Emmy Noether. Her theorem states that for every continuous symmetry in the laws of nature, there is a corresponding conserved quantity. This is a stunningly elegant concept. A symmetry means that when something changes, the system itself remains the same. The laws of physics are the same today as they were yesterday. From this time symmetry Noether's theorem proves that energy must be conserved. The laws of physics are the same here as they are on the other side of the galaxy. From this spatial symmetry the theorem proves that linear momentum must be conserved. The laws of physics have no preferred direction. From this rotational symmetry the theorem proves that angular momentum must be conserved. This is a monumental realization. The reason reality is predictable is because its fundamental laws are symmetrical. The stability we rely on is a direct consequence of the universe's indifference to when, where, or in what direction events occur. These laws are the guardrails of reality. This leaves one final question. If the subatomic world is governed by probability, and the macroscopic world by these deterministic laws, where is the boundary? How does the fuzzy quantum world become the solid, predictable classical world? The transition is a process known as quantum decoherence. A quantum system, like an electron, exists in a superposition of many states only when it is perfectly isolated. In the real world, nothing is ever truly isolated. A single atom is constantly being bombarded by air molecules, stray photons, and thermal vibrations. Each interaction is a form of measurement. It is the environment peaking at the quantum system. Every time the environment interacts with the particle, it leaks information about the quantum state out into the wider world. This constant, unavoidable interaction destroys the delicate superposition. The particle's wave of possibilities collapses into one single, definite, classical state. The quantum weirdness, like being in two places at once, is averaged out on a massive scale. This process is astonishingly fast. For a macroscopic object, interactions with the environment collapse its quantum superposition almost instantaneously. We never see a chair in two places at once because the environment is constantly forcing it to choose a single, classical reality. Decoherence is the process that connects the probabilistic quantum world to the deterministic one we experience. It is not that quantum laws stop working for large objects. It is that their effects are washed out by the ceaseless noise of the universe. Now we have a more complete picture. The stability of reality is a multi-layered construct. At the bottom, the fuzz of quantum fields. Imposing order are the Pauli exclusion principle and electromagnetism, creating structure. Governing behavior are the conservation laws, born from symmetry. And constantly policing the boundary is decoherence, ensuring large objects behave in the definite ways we expect. The solid world is not the default state. It is an emergent property, a statistical certainty arising from countless quantum interactions, all governed by unbreakable rules. We have journeyed from quantum chaos to the orderly laws of the cosmos. We have seen how invisible forces and principles construct a reliable reality from a foundation of uncertainty. But there is one final, crucial piece to this puzzle: our own perception. Modern neuroscience suggests the brain operates as a prediction machine. It does not passively receive sensory data. Instead, it actively and constantly generates its own model of the world, using sensory input to update and correct that model. The light hitting your retina is just a collection of photons. The vibrations in the air are just pressure waves. Your brain takes this noisy, ambiguous data and constructs a rich, stable world filled with solid objects and a coherent flow of time. That feeling of solidity is also a neural construct. Your brain has learned from a lifetime of experience that when you push on a table, it pushes back. It has built a powerful predictive model. Objects with these properties are solid. They cannot be passed through. When you see a mug on a desk, your brain doesn't just register a pattern of light. It instantly predicts its weight, its hardness, its function. You experience the asterisk solidity of the mug before you touch it. The world feels stable because your brain is wired to assume it is. But the brain does not invent this stability. It builds these predictions because the underlying physics is incredibly reliable. Your brain predicts the table will be solid because the Pauli exclusion principle and electromagnetism have never once failed to make it so. It predicts a dropped object will fall because the law of conservation of energy, born from the universe's time symmetry, is unbreakable. Our perception is an evolutionary adaptation to the stable physics of reality. Our minds have evolved to reflect the stability already present in the universe's fundamental laws. The perception of solidity is the brain's efficient, shorthand summary of a complex quantum negotiation. When you touch a wall, your brain simply gives you the bottom line: solid. It is a user interface for reality, hiding the staggeringly complex code of physics beneath. This is why illusions are so compelling. They work by violating your brain's predictive models. The feeling of surprise is your brain's prediction engine encountering an error and scrambling to update itself. The solidity of reality is a duet between the external world and our internal one. The universe provides the unyielding physical laws. Our brains, in turn, create a perception of that stability that is immediate, intuitive, and unshakable. The illusion of solidity is not a lie. It is a simplified representation of a much deeper and more magnificent truth. We come full circle. You are composed almost entirely of empty space, and yet you are undeniably, tangibly here. You do not fall through the floor, not because the floor is full, but because the floor is governed by rules. The universe is built on a foundation of shimmering, probabilistic chaos, but it is not a lawless realm. It is a reality policed by invisible but absolute forces. Electromagnetism acts as a repulsive shield. Behind it stands the Pauli exclusion principle, a quantum law forbidding matter from sharing the same space, giving it structure and volume. These structures behave predictably, guided by the grand conservation laws, which are themselves a consequence of the fundamental symmetries of our universe. Finally, decoherence washes out quantum strangeness at our scale, while our brain constructs a seamless perception of this reliable world. The feeling of solidity is not a property of matter. It is the palpable sensation of physical law. It is the feeling of fundamental principles pushing back. The next time you knock on a door or lean against a wall, remember what you are truly experiencing. You are pressing against an invisible force field woven from the mathematics that underpins existence. You are interacting not with stuff, but with the elegant and powerful enforcement of cosmic order. And in that stability, born from chaos, we find evidence that normal was never the plan. A choice is made. Your finger moves, the cursor aligns, and a story begins. It felt like a choice, simple and free. An expression of your will. But what if that feeling, of being the author of your own actions, is just the final, quiet ripple from a deep and ancient current? What if, many seconds ago, a pattern of activity began to form deep inside your brain, making it so that you would be here, right now? What if your choice was simply the last piece to fall into place, in a line that started long before you were even born? This isn't a riddle. It is a journey backwards in time, following the story of that single choice you just made. We will trace it from the neuron that moved your finger, back through the minutes, days, and years of your life. Back through your childhood, and into the stone and code of your genetic history. This is the story of how the universe flows through us, and how the feeling of control might be the most powerful illusion we have ever known. To understand the story of your click, we have to travel backwards from the moment it happened. Let's call it time zero. In your experience, the thought came first, "I'll watch this," and then the action followed. It feels simple, but this is where the world we think we know begins to feel unfamiliar. In the 1980s, a scientist named Benjamin Libet designed a beautifully simple experiment. He asked people to do something small and voluntary, just flexing their wrist whenever they felt the urge. They were also asked to watch a special clock and note the exact moment they first felt the conscious intention to move. While this was happening, Libet was watching their brain activity. He was looking for a signal called the readiness potential, which is a buildup of neural activity that comes before a voluntary movement. The question was simple. Which appears first? The brain's preparation to act, or our feeling of deciding to act? The answer was strange, and we are still talking about it today. The brain's readiness potential began to build about 550 milliseconds before the wrist moved. But the person's awareness of their decision? That only appeared about 200 milliseconds before the action. For a gap of about 350 milliseconds, the brain had already begun the process of moving, all before the person felt like they had made a choice. Think of what that means. The conscious feeling of choosing, the part we call I, wasn't the origin of the action. It was more like an announcement that the process was already underway. The brain begins the story, and then it informs you of the plot. The conscious mind isn't the king, issuing commands. It's more like the narrator, reading from a script that has already been written. Libet's experiments were the first of their kind, But the story they told has been told again and again, with newer technology. Using modern brain scanners, scientists at the Max Planck Institute could see patterns of activity that predicted which hand a person would choose to press a button with. This prediction was possible up to 7, sometimes even 10 seconds before the person themselves knew what they were going to do. The accuracy was not perfect, hovering around 60%, but it was consistently better than chance. It's as if our decisions are prepared by brain activity long before our consciousness is invited into the room. By the time it arrives, much of the work has already been done. The feeling of deciding isn't the cause. The feeling of deciding is part of the effect. So, the click that brought you here? Perhaps 7 seconds before you were aware of it. A pattern of blood flow and firing neurons deep within your brain already held the shape of what was to come. The thought, "I think I'll watch this," was just the surface ripple from a wave that started in the deep. The first part of our journey shows us that our conscious self was one of the last to know about the choice it believed it was making. But what caused that wave? To find out, we have to travel further back. The state of your brain 7 seconds before the click was not born from nothing. It was the product of everything that happened in the hours and days that came before. The mind that made the decision was shaped by 1,000 quiet influences you were likely not aware of. There is an old saying that justice is what the judge had for breakfast. It turns out there is a real story behind this. A well-known 2011 study examined over 1,000 parole decisions made by judges. They found a strange pattern. At the start of the day, the chance of a prisoner receiving a favorable ruling was around 65%. As the hours passed, that number slowly dropped, getting close to 0 just before the judge's next meal break. Then, right after the break, it jumped back up to 65% and began its slow descent all over again. The judges were not aware of this. They were professionals, making choices based on the facts. But the biological state of their bodies, their blood sugar, their mental fatigue, was shaping their decisions. A tired and hungry brain defaults to the simpler, safer choice: no. Now think of yourself, in the moment you saw this video. Were you stressed? High cortisol levels push the brain toward habit and away from curiosity. Were you hungry? Low blood sugar can make us impatient. Or had you just eaten? A quiet surge of dopamine making you feel open and receptive? Each of these internal, biological states changed the landscape of your mind. They made some neural paths easier to walk down than others. The light in the room, the sounds in the background, all of these things were being processed, gently pulling and pushing the probabilities of your next action. The choice was not made in a sterile room of pure reason. It was made by a living body, swimming in a complex chemical soup whose recipe was written by the last 24 hours of your life. Your brain in that moment was like a complex equation. The variables were your hormones, your hunger, your tiredness, your surroundings. You did not choose these variables. They were the given circumstances of your biology. And they all worked together to create the neural activity that would, seconds later, look like a choice. We have gone from seconds to hours. But the way your brain was built goes much deeper. For that, we must go back years. Why does one person react to a new idea with curiosity, and another with anger? The answer is in the architecture of the brain itself. An architecture slowly built, day by day, over a lifetime. From the moment we are born, our world begins to shape us. An infant's brain is a vast, unpruned garden of possibilities. As we grow, the connections that are used become stronger, while those that are ignored wither away. The language you speak, the faces you know, the rules of your culture, these things become physically part of your brain structure. If you grew up in a home that valued debate, the parts of your brain for reasoning grew strong. If you grew up in chaos, your amygdala, the brain's center for fear and threat, may have become more sensitive. This is not a metaphor. It is physical reality. Childhood trauma can leave a literal mark on the brain, creating a hyper-reactive loop that is always watching for danger. Your education, your friends, the media you consumed, the values of your community. Every input acted like a sculptor, carving the channels that your thoughts would flow through for years to come. So when you saw the title of this video, you did not see it with new eyes. You saw it through the filter of a lifetime. A lifetime that may have taught you to trust science, or to be skeptical of it. A lifetime that may have taught you about individual will, or about the power of circumstance. The neurobiologist Robert Sapolsky describes it as an unbroken chain. The state of your brain a second ago was determined by the hour before. The way your brain responded was shaped by the structures built during your youth. The structure of your young brain was shaped by your childhood. Your childhood was shaped by the world you were born into. Every cause has a cause before it. You are the sum of all the things you did not choose. Your childhood, your culture, the values you were taught. All these things came together to build the unique machine that is your brain. And that machine, when given the input of this video, produced an output. It was the only output it could produce, given its specific, unchosen design. You did not choose to be the person who would click, or the person who would scroll past. You simply were that person. But the chain does not stop there. The very blueprint for the brain you were born with was also something you did not choose. To find that link, we had to go back to a time before you were you. Before your first breath, the lottery was played. This was your genetics. The unique combination of DNA from your parents laid the foundation for the person you would become. Your genes influenced the sensitivity of your dopamine receptors, shaping your experience of pleasure and motivation. They influenced your baseline mood and impulsivity. They dictated the basic architecture of your nervous system, how prone you are to anxiety, how you respond to stress, whether you lean toward introversion or extroversion. Genes are not destiny. They are more like preliminary sketches. They don't say, you will be anxious, but rather, in a stressful environment, you are more likely to become anxious. They set the initial conditions, the raw material that your life's experiences would then shape. You did not choose these genes. They were dealt to you. And where did they come from? From an unbroken chain of survival stretching back billions of years. They are the legacy of every ancestor who lived long enough to pass them on. The very structure of the human brain is a product of this deep, ancient history. We have brains that see patterns, even when there are none. We have brains with a powerful negativity bias, because for our ancestors, it was better to mistake the wind for a lion than a lion for the wind. We are the descendants of the anxious ones, the ones who survived. This inheritance explains so much of our modern world. Our tribalism, our fears, our craving for sugar and fat. And so the causal chain is complete. The click was the result of your brain state seconds before. That brain state was the result of the hours before. The way your brain processed it all was the result of a lifetime of shaping. The initial blueprint for that brain was the result of your genes. And your genes are the result of millions of years of evolution. From the dawn of life to the click of a mouse, it is one long, unbroken story. Each link forged by the one that came before. At no point in this chain was there a place for a magical, uncaused, you, to step in and change its direction. You are not a ghost in the machine. You are the machine. A biological machine of incredible complexity, but a machine nonetheless. This idea can feel wrong. Our deepest experience is one of freedom. We feel that we weigh options and make choices. In the face of this long chain of causes, many people turn to two places to find a crack in the argument: the strange world of quantum physics, and a confusion about what determinism truly means. The first idea is about quantum mechanics. At the smallest scales of reality, things are not so predictable. Events are governed by probability, not certainty. Perhaps this randomness, at the very heart of the universe, is the space where free will can live. It's a beautiful thought, but it may not hold. First, there's little evidence that these tiny quantum events have a meaningful impact on something as large as a neuron. The brain is a warm, wet, noisy system that seems to operate by the rules of biology, not quantum weirdness. But even if it did, randomness doesn't give you freedom. It just gives you randomness. If your choice was caused by a random particle swerving in your brain, how is that your choice? An action caused by chance is no more free than an action caused by a chain of events. It is just a twitch in the system. The second objection comes from confusing determinism with fatalism. This is perhaps the most important distinction. Fatalism is the belief that an outcome is set, no matter what you do. The myth of Oedipus is fatalistic. Everything he did to avoid his fate only led him to it. This implies your choices are irrelevant. Determinism is a different idea entirely. It doesn't say your choices are irrelevant. It says your choices are a asterisk part of the causal chain. Your choices matter. They are the very way the future happens. A fatalist says, it doesn't matter if I study, I'm destined to pass or fail. A determinist says, the outcome is determined, and a critical part of what determines it is the process called studying. Your deliberations, your efforts, your struggles, they are all crucial links. A person who gives up creates a different future than a person who strives. But the striving itself was also caused. You didn't choose to be the kind of person who strives. You were made that way by your genes and your life. Your actions are not separate from the flow of the universe. They are the leading edge of its unfolding. If we are not in control, what happens to responsibility? To praise and blame? If a person's actions were the inevitable result of their brain, their genes, and their past, does it make sense to hate them? And here we arrive at the quiet, human heart of this idea. Fully accepting this story does not have to lead to despair. It can lead to a world with more compassion. We do not blame a person for having cancer. We do not blame a car for having a broken engine. We see these as biological or mechanical failures. We may work to fix them or protect ourselves from the harm they cause, but we do not feel hatred. Accepting that human behavior is the output of a biological machine allows us to take the same approach with people. It allows us to move away from a justice system based on retribution, the idea that people deserve to suffer, and towards one based on keeping society safe and trying to help. We can still see that some people are dangerous. But we can see them not as evil agents who chose their path, but as the unfortunate end product of a tragic story. This doesn't mean nothing matters. It means that everything that causes us to be who we are matters immensely. It places a profound importance on creating better environments, on alleviating poverty, on healing trauma. Because these are the inputs that will build better brains and cause better futures. It also changes how we see success. If someone achieves great things, we can still admire their talent. But the idea that they deserve their rewards in a deep moral sense fades away. They were lucky. Lucky in their genes, their upbringing, their opportunities. This understanding brings humility to the successful, and removes shame from the unsuccessful. But what about change? If we are determined, can we improve? Yes, but we are changed by new inputs. A book can change you. A conversation can change you. This very video, by offering new information, is a causal force acting on your brain right now, gently altering the probabilities of your future thoughts. Change is constant. We are systems that can be transformed by experience. The goal, then, becomes to seek out the experiences and the information that will shape us into the people we hope to become. This idea can be unsettling. It asks us to step down from the pedestal we built for ourselves. But in its place, it offers something more valuable. A release from the weight of blame, a deeper capacity for forgiveness, and a stronger reason to build a better world, not because we feel we should, but because we understand that by improving the lives of others, we are shaping the future for the better. We do not roam free in reality. We walk paths that were drawn long ago. But understanding the map allows us to navigate it with more wisdom and with less judgment. This is a monumental shift in perspective. It challenges our most basic feeling about who we are. So, I want to ask you, What is one choice you've made in your life that you now see differently through the lens of this long causal chain? What does it feel like to consider that, perhaps, it could not have gone any other way? Share your thoughts below. This is a conversation that goes to the core of our story, and it's a conversation worth having.